Today, we are answering an age-old, very scientific and important question. What if the moon crashes into Earth? It's more interesting and weird than you probably think. Let's start with the basics. Why isn't the moon on its way to crash into us already? We know that Earth's gravity pulls everything towards it, including the moon, but somehow it stays up, as if suspended by some opposite force. But there is no other force countering gravity. Instead, the trick to staying up is a sideways motion that we call an orbit. You see orbits every day. When you throw a ball, it makes a tiny little orbit. The only difference between the ball's orbit and the moon's is that the ball eventually hits the ground. Basically, the reason is speed. If you could throw your ball fast enough, it would bend around the world and come back to you. If there were no air slowing it down, it could orbit forever. And this is what the moon does, falling sideways around Earth very fast with no air slowing it down, orbiting Earth every 27 days at 3,600 kilometers an hour. So, for the moon to just stop in its orbit and plummet to the Earth would break more laws of physics than we have time to explain. So, how do we crash it into Earth? In a nutshell, to change an object's orbit, you need to change its speed, which changes where gravity takes it. But even small changes require enormous forces, which is why all the large objects in the solar system are so stable nowadays. According to science, the moon is big and very massive. Even igniting billions of rocket engines all over its surface would barely move the moon. It looks like nothing short of magic will make the moon fall, so we'll use a magic spell that slows down the moon so much that it changes its orbit and spirals towards Earth. To get the most from the experience, the moon will take exactly 1 year before it hits Earth. Ready? 3, 2, 1. Magic. Month 1. For the first few days, nothing really changes. The moon gets a tiny bit brighter and scientists get confused, but the rest of us don't notice anything different. The only noticeable real effect of the moon on the Earth are the tides. Tides exist because while Earth pulls on the moon's gravity pulls back on the Earth. Since the strength of gravity gets weaker with distance, different parts of the Earth feel a slightly different pull, which causes the Earth, especially the oceans, to bulge when the moon is above them and contract a little on the sides when it's not. As Earth rotates every day underneath the moon's influence fluctuates, causing the water level of the oceans to rise and fall by about half a meter twice a day. But with the moon drawing ever closer, high tide gets higher every day. At first barely noticeable, within a month the moon has covered half the distance to the Earth and ocean tides have grown to 4 meters. Every day high tide comes and waves flood coastal cities. And there's no end in sight. With the moon drawing ever closer, tides rise ever higher, inundating another city and more inhabited land with salty water every day. Month 2. By the end of month 2, the moon has covered 2/3 of the distance to Earth and global infrastructure is crumbling as tides rise above 10 meters, displacing up to 1 billion people who happen to live near the coastlines. As ports become inoperable, shipping grinds to a halt. Not only will it slow down the delivery of Kurzgesagt products, but also less exciting things like food. Global communications fall into disarray. 95% of the internet is carried by ocean-crossing cables, and while these largely don't mind the water, their terminals on land do. Living inland doesn't guarantee safety either. Tidal bores cause rivers to flow backwards, carrying salt water to contaminate surface and groundwater supplies. Gas shortages follow as oil refineries near the coast are abandoned. Countries are left with the supplies they had on their shelves, and strict rationing will begin. In the cities, chaos reigns during the scavenging hours of low tide, while survivors take refuge in high-rises when the water returns. Month 3. 3 months in and the moon is close enough to disrupt communication and navigation satellites. While it's normally far too distant for its gravity to cause any major problems for our satellites, the closer it gets, the more warped their orbits become. As their fuel for orbital corrections runs out, satellites careen out of control. Months 4 and 5. On Earth, the tides are rapidly growing to about 30 meters and will be reaching 100 meters in height in a few short weeks. At low tide, the ocean recedes hundreds of kilometers, exposing the continental shelf like vast deserts, while at high tide, walls of water drown agriculture, houses, and skyscrapers. And now, almost 5 months in, the apocalypse has finished its warm-up act. Since the oceans are on average only 3 kilometers deep, the tides have reached their maximum. Up until now, the water in the oceans could flow, absorbing most of the moon's gravitational squeezing, but now the Earth itself is really feeling the squeeze of the ever-approaching moon. These aren't so much tides of water, but tides of rock. The squeezing of the planet, combined with the weight of quintillions of tons of water sloshing on and off the tectonic plates, creates enormous stresses below and begins to cause earthquakes of increasing magnitude and intensity. It's impossible to say how serious these earthquakes might be or where they occur, but like a child jumping on their bed until it breaks, no good can come of it. Strong tidal forces lead to volcanism on other planets and moons. On Earth, squeezing the planet disrupts the magma reservoirs inside the crust, triggering sizable, climate-altering eruptions in Chile, New Zealand, Yellowstone, and elsewhere. Meanwhile, watching patiently above is the moon. Still no bigger in the sky than a small cloud. Within 75,000 kilometers of Earth, it is bright enough to illuminate the night sky like twilight. Months 6 and 7. After half a year, the moon is entering the space once occupied by geosynchronous satellites, where it orbits Earth every 24 hours. It appears to float at one spot in the sky, unmoving, cycling through a full set of phases every day, but only visible to half the planet. With the moon stationary above the Earth, the tides seem to freeze in place. Half the world flooded, half with its water seemingly returned to the sea, as if Earth is holding its breath to prepare for the worst. As the moon sinks further, you might wonder if its gravity would overpower Earth's, pulling you up and ending your misery. Fortunately not. The Earth's surface gravity is about 6 times stronger than the moon's, so even if the moon were hovering right on top of you, you would still stay on the ground. On the moon, things are different though. The near side of the moon is more strongly affected by Earth's gravity, so during the next few months, it starts to stretch forward towards the Earth into something of an egg, triggering deep moonquakes as the lunar rock flexes and changes shape. Though barely noticeable now, this squish will grow to hundreds of kilometers in a matter of months. Months 8 to 11. At this point, the apocalypse has arrived, and we can summarize the months before the crash as everybody left has a really bad time. The tides sweeping over the Earth slow down and then reverse their direction because the moon now orbits Earth faster than it rotates. The planet will experience an abundance of earthquakes and volcanism. Massive amounts of volcanic aerosols rise high into the stratosphere, shiny enough to reflect sunlight back into space. What little light gets through is rust red and is periodically diminished by daily eclipses. The result is a rapid global cooling with acid rains and summer snows killing even the hardiest plants. The clock runs out on civilization. Billions have perished while an X-shaped moon is still drawing closer. Let's get ready for the grand finale. Month 12. Finally, at the end of the year, the moon has reached the Roche limit. That's the point where Earth's gravitational pull on the moon is stronger than the moon's own gravity. Things on the lunar surface start falling towards Earth, and by the time it crosses 10,000 kilometers, the entire moon disintegrates into rubble, smearing itself into a massive ring system around the Earth. Fortunately, the moon's disintegration means the misery on Earth has ended. No moon means the general apocalyptic nature of things comes to a halt. The oceans recede, flowing off the land one last time. Any survivors are treated to a view of tremendous arches spanning the sky, glimmering in the sunlight, illuminating the night sky more brilliantly than any full moon ever could, while meteor showers of moon dust fill the sky. It's hard to say what happens next, but the tranquility may be short-lived. If too much moon dust rains down, friction heats the atmosphere, possibly boiling the oceans. If not, the enormous shadows cast by the rings, combined with all the volcanic and meteoric aerosols, block even more sunlight and a period of runaway cooling could begin that freezes much of Earth's surface solid. In any case, at some point people will emerge again, from submarines or bunkers or mountain tops. They will not have a great time before rebuilding civilization, and their success is not guaranteed, but at least they'll be trying to do so with beautiful rings in the sky. Black hole stars may have been the largest stars that ever existed. They burned brighter than galaxies and were larger than any star today or that could ever exist in the future. But besides their scale, what makes them special and weird is that deep inside, they were occupied by a cosmic parasite, an endlessly hungry black hole. How is that even possible? Black hole stars take the weirdness of black holes and go beyond to break everything we know about how stars form and grow. They were only possible during a short window of time in the early universe, but if they existed, they would solve one of the largest mysteries of cosmology. Black hole stars were excessive any way you look at them. The most massive stars today may have about 300 solar masses. A black hole star had up to 10 million solar masses of nearly pure hydrogen. Let's take a moment to look at what this means visually. The Sun, Wesen, LL Pegasi, the largest star, and finally the black hole star. Its scale is beyond words. Over 800,000 times wider than our Sun, 380 times larger than the largest star we know today. And far below its surface is a black hole, growing rapidly as it devours billions upon billions of tons of matter per second. Normally, stars are born from gigantic clouds, collections of thousands or millions of solar masses of mostly hydrogen. In these clouds, matter starts to accumulate around the densest spots inside. As these spots get denser, their gravitational pull intensifies and they grow faster. Eventually, they generate so much heat and pressure that they ignite fusion reactions and a new star is born. But this puts a limit on their size. Nuclear fusion releases enough radiation energy that the surrounding gas cloud is blown away. The new baby star can't gather more mass. From now on, the star is living on the edge between two forces: gravity pulling in, trying to squash the star, and radiation created by fusion pushing outwards, trying to blow the star apart. After millions or billions of years, the core runs out of fuel and the balance breaks, destroying the star. But black hole stars were very, very different. The beasts of the early universe. A few 100 million years after the Big Bang, when the universe was much smaller, all the matter in existence was much more concentrated. The universe was much denser and hotter. Dark matter was a dominant player, forming giant structures called dark matter halos. These dark matter halos were so massive that they pulled in and concentrated unimaginably gigantic amounts of hydrogen gas, becoming the birthplaces of the first stars and galaxies. Epic clouds of hydrogen formed, some as massive as 100 million suns, more than the mass of small galaxies. In this unique environment that will never exist again, the enormous gravitational pull of the dark matter halos drew gas into its center and created extremely massive stars. As we said before, when a star is born, it blows away the gas cloud that created it. But these titanic gas clouds in the early universe were so large and massive that even after their birth, more and more gas piled on the newborn star, making it grow to unbelievable proportions. The young star is forced to grow and grow and grow, getting more and more massive, until in some cases it reaches up to 10 million times the mass of our Sun. Crushed by gravity, its core gets hotter and hotter, desperately pushing outwards, trying to blow itself apart, but to no avail. There's too much mass and too much pressure. The balance is impossible to uphold. Like a supernova on fast forward, the core gets crushed into a black hole. Normally that would be the end. Today's stars go supernova, a black hole forms, and things calm down. But in this case, the star survives its own death. A tremendous explosion rocks the star from the inside, but it's not enough. The star is so large and massive that not even a supernova can destroy it. But now it has a black hole for a heart. It's tiny, a few tens of kilometers in the center of a thing the size of the solar system. The monster grows. Stars are born from ever faster spinning and collapsing gas, and so they also spin. When a black hole is born from the core of a star, it keeps its angular momentum. This means that matter that gets drawn in doesn't just fall in a straight line, but instead begins orbiting the black hole, in smaller and smaller circles, going faster and faster. The result is an accretion disk where gas orbits at nearly the speed of light. Only a small amount of gas actually falls in at any given moment. Basically, black holes put a lot of food on the table and only nibble at it. But the matter trapped in the accretion disk doesn't have a good time. Friction and collisions between particles heat it up to temperatures of millions of degrees. Actively feeding black holes have accretion disks that are incredibly hot and powerful. This heat from the disk further restricts how much a black hole can devour, just like the core of stars. The super-hot material creates radiation that blows away most of the food within its reach. So even if a black hole had access to as much food as it desired, it can only grow slowly. A black hole embedded inside a black hole star is different. The enormous pressure surrounding it pushes down matter directly into the black hole, overcoming all restrictions on how fast it can consume. This process is so violent and releases so much energy that the accretion disk becomes hotter and releases more radiation pressure than any star core ever could. Enough to push back against the weight of 10 million suns. An impossibly dangerous balance has been created. Millions of solar masses pushing in, the angry radiation of a force-fed black hole pushing out. For the next few million years, the black hole star is consumed from within. The black hole grows to thousands of solar masses, and the bigger it gets, the faster it eats, which heats up the star even more and causes it to expand. In its final phase, the black hole star has become over 30 times wider than our solar system, truly the largest star to ever exist in the universe. The intense magnetic fields at its core spew out jets of plasma from the black hole's poles, which pierce through the star and shoot out into space, turning it into a cosmic beacon. It must have been one of the most awe-inducing sights to ever exist in the universe. But this also marks the end. It becomes too stretched, and the accretion disk within too powerful. The parasite destroys its host, blowing it apart. A black hole with the mass of 100,000 suns rips its way out to hunt for new prey while leaving behind nothing but a star carcass. The supermassive question. If black hole stars existed, they could explain one of the greatest mysteries of the universe. The supermassive black holes we see at the center of galaxies are just too big. They shouldn't be possible. Black holes born from regular supernovas can be a few tens of solar masses at most. And because of the process we explained before, they grow slowly after that. If black holes merge, they can form slightly larger black holes of over 100 solar masses. It should take billions and billions of years to make black holes with hundreds of thousands or even millions of solar masses. And yet, we know that some supermassive black holes already had 800 million solar masses only 690 million years after the Big Bang. Black hole stars are a sort of black hole cheat code. If they formed very early in our universe, and the black holes that emerged from them were thousands of solar masses, then they could be the seeds for supermassive black holes. These seeds could take root in the center of the earliest galaxies, merging with others and drawing in enough matter to grow quickly and reliably. Very soon, we may be able to verify their past existence. The James Webb Space Telescope is turning its sensors to explore the farthest reaches of the universe, looking back in time, back to the early universe that we couldn't see before. So, with luck, we might be able to witness glimpses of these tragic titans in the brief moment between their formation and destruction. Until then, let's do the visual journey again, just for fun. Stars are big. Black hole stars bigger. How big is the Moon? In the night sky, the Moon seems rather small, but in reality, it really isn't. Central Europe would easily fit under it. The surface area of the Moon is huge. To give you some perspective, it's as big as the whole European continent, China, the USA, Brazil, and South Africa together. Weight-wise, the Moon is only about 1/81th of the mass of Earth. But how big is it in relation to Earth? Quite big, actually. Our Moon is the biggest in the solar system in relation to its planet, and it's the 5th largest moon in the solar system, quite a bit bigger than the dwarf planet Pluto. Now, if the Moon is really that huge, how far away is it from us to seem this small in the night sky? 370 kilometers, as far as the ISS maybe? No, at that distance, gravitational forces would rip the Moon apart. At 36,000 kilometers, it would be as far away as our most distant satellites. Let's adjust the distance to reality. Pretty far away, right? A 747 would need 28 straight days to fly to the Moon, and even with our current technology, we'd need 2 full days. And in a car, a lot of time. So, how big is the Moon? Well, it kind of depends how you define big. But seriously though, it's pretty big. Humans can survive in this universe as long as we have an energy source. Unfortunately, the universe will die. It will happen slowly, over many billions of years, but it will happen. On a universal timescale, stars like our Sun will be gone in no time. Luckily, there are places that will exist practically forever from a human perspective. The corpses of dead stars. White dwarfs. They could be humanity's last home right before the death of the universe. What are these strange things, and what happens when they finally die? How long stars live varies drastically, depending on how massive they are. For example, really massive stars burn hot and fast, dying violently in supernova a few million years after birth. But they're the exception. 97% of all stars will end their existence as white dwarfs. There are 2 ways this can happen. Small stars, so-called red dwarfs, burn out over trillions of years until they eventually quietly turn into white dwarfs. Medium-sized stars like our Sun are more interesting. Imagine the Sun as a huge pressure cooker that fuses hydrogen into helium in its core through its gravity. The fusion of elements releases extreme amounts of energy that pushes outwards and stabilizes the star, keeping it in a delicate balance. When the Sun is old, the hydrogen in the core is exhausted, and the Sun will begin to burn helium into heavier elements. While doing so, it will shed its outer layers. When this process is over, more than half of the Sun's mass will be lost into space as a spectacular planetary nebula millions of kilometers across. What remains will be its former core. A white dwarf is born, a star corpse. While its former self was about 100 times its diameter, now it's only about as big as Earth, but still with about half of its former mass. This means it's extremely dense. A teaspoon of white dwarf is about as massive as a car. Its surface gravity is over 100,000 times higher than Earth's. If you tried to land on it, you'd immediately be compressed into a steaming puddle. Life around a white dwarf is very unlikely, but possible. Most of them that exist now were former stars that, well, died, which probably ruined any planets they once had. But that's not all. Since they are so small, a planet would need to orbit them about 75 times closer than Earth is to the Sun to have liquid water. This proximity has up and downsides. For one, it would tidally lock the planet, giving it a permanent day and permanent night. At the edges of these day and night zones, life could be possible. But white dwarfs have a very stable energy output, so they might actually be safer to live around than many red dwarfs. This is still speculation at this point, but if we could find a white dwarf with the right conditions to settle around, we could have a home for many billions of years. But why do they shine so much longer than other star types? White dwarfs are very, very hot, up to 40 times hotter than our Sun, ranking among the hottest objects in the universe. But they are not incredibly active. All the heat inside of them is trapped and has nowhere to go. Only on its outer layer can it escape into space. But space is mostly empty, so heat can't be transferred by conduction. The only way energy can escape is by radiation. This is so inefficient that white dwarfs will take trillions of years to cool down, which may make them humanity's last refuge. They might be the last sources of light and energy in a dying universe. According to some estimates, white dwarfs might shine as long as 100 billion years, 10 billion times longer than the universe has existed. So far into the future that no regular stars will shine anymore. Galaxies will have evaporated. And only then will the first white dwarf turn into the first black dwarf. When this happens, the last hope for life will die off. Black dwarfs will be inactive spheres with no energy left to give. Still massive enough to kill you if you get too close. So cold that they'll be near the coldest possible temperature in the universe. So dark that they are practically invisible. The universe will enter its last stage, heat death, which will leave the universe unrecognizable. An absolutely dark and cold graveyard with black holes and black dwarfs scattered over trillions of light years. We don't know for sure what will happen with black dwarfs in the end. If the proton, one of the fundamental parts of atoms, has a limited lifespan, black dwarfs will slowly evaporate over many trillions of years. If the proton does not decay, black dwarfs will probably turn into spheres of pure iron via quantum tunneling over a time span so obscenely gigantic that calling it forever is okay. These iron spheres will then travel completely alone through a dark universe. Nothing new will happen anymore. Forever. While this may sound kind of dark, this is so far away that for our purposes today, it might as well not happen at all. It doesn't matter what happens in a billion trillion years. Right now, we happen to exist at an excellent time, able to be in awe about a universe filled with endless stars and light and planets, and enough time to visit them one day. What would happen if we were to detonate a very, very powerful nuclear weapon on the Moon? Would the explosion knock its orbit towards Earth, causing tidal waves and misery? Could the Moon be destroyed, showering the Earth in a rain of meteoric death? During the Cold War, the Moon was a major target for space exploration and, military bases. So, the US Air Force commissioned a serious study into the effects of a nuclear detonation on the surface of the Moon. But just quoting stuff is boring, so let's conduct a very important scientific experiment with an imaginary 100 megaton thermonuclear warhead about twice as powerful as the most powerful bomb ever detonated. We'll also place a number of curious astronauts around the Moon as observers. Let's push the button and slow down time. For the first few milliseconds, nothing much happens outside our weapon. Meanwhile, inside, high explosives send a shockwave to a radioactive metal core, compressing it so much that it reaches criticality and starts a nuclear fission chain reaction. The 100 million degree plasma created in this first stage sets off the second stage with atomic nuclei fusing like they do in the core of a star. Very briefly, our weapon contains one of the hottest places in the universe. And only now, barely 10 milliseconds later, does the rest of the universe find out that anything has happened, as suddenly the bomb dissolves and a flaming star of nuclear death is born. So far, so good. But everything that happens now is very different from what we're used to on Earth because of one major difference. There's no atmosphere. As the fireball shines, it releases a flash of X-rays and thermal photons, a wave of silent heat which rushes outwards in all directions. On Earth, this heat would char and burn everything within a 50-kilometer radius at least. But on the Moon, without an atmosphere and oxygen-rich air, there's no burning at all. Also, there are no things to burn. The crunchy topsoil of the Moon is made from silicate rock and metals chewed to dust by eons of meteorite impacts mixed with tiny traces of water. When heated by the explosion, X-rays from the fireball vaporize a thin cloud of rock from the lunar surface, while the unlucky dust that's inside the fireball melts into glass. Any astronauts watching the show within about 50 kilometers can expect to be fried. And now we begin to see one of the biggest differences between explosions in space and on Earth. On Earth, the atmosphere fights back against the plasma bubble. Its expansion is violently stopped within moments by the pressure of the atmosphere. But this is not good news. As the fireball rams the atmosphere, it produces the most destructive part of a nuclear explosion on Earth, the shock wave. Compressed air around the explosion rushes out faster than the speed of sound, shattering buildings and roaring so loud it ruptures organs. But on the Moon there is no shock wave. No atmosphere means nothing to impede the expanding explosion in space. On the Moon, the fireball just grows in eerie silence as there's no atmosphere to stop it or to give it a voice. This would be an amazing thing to watch from a safe distance. Unfortunately, there's hardly any safe viewing distance for a nuclear explosion on the Moon. Without an atmosphere weakening the deadly ionizing radiation that can scramble DNA, anyone close enough to get a good look will be exposed to fatal amounts of radiation. But of course, that's not all. While all of this happens, the explosion hammers against the Moon, transferring about 1/10 of the explosion energy into seismic waves, powering an intense moonquake. The Moon is much smaller than the Earth, and our astronauts will feel an inescapable violent shaking no matter where they're standing. Comparable to an earthquake of 7 on the Richter scale, this shaking could seriously damage or even level infrastructure we might have built anywhere on the Moon. Those who hid on the far side of the Moon would have no idea it was an explosion. The quaking would feel like an asteroid the size of the Great Pyramid had struck. And it's not over yet. Where our bomb explodes, the ground splatters like water when a rock strikes a pond. As the explosion pushes against the surface, it may excavate as much as 100 million cubic meters of dust and rock, forming a crater 1 kilometer across, while bedrock is pulverized to rubble. Debris is shot into the sky in every direction. Again, without an atmosphere, there's no drag to slow any of it down. Much of the debris scattered never returns to the Moon, flying off faster than escape velocity. A flurry of micrometeorites have been cast off to explore the solar system, many of which will rain down on the Earth, though few will be larger than pebbles. Any satellite, astronaut or space station in the way, though, will have a really bad time. Micrometeorites are launched at many speeds and angles, allowing them to spread all over the surface of the Moon. Like bullets, they'll punch through our curious astronauts no matter where they stand. Finally, our explosion comes to an end. On Earth, the fireball rises like a hot air balloon, forming a sort of stalk. As it reaches up, cooler air is drawn in around it, rounding the top into a mushroom cloud. But on the Moon, well, you know by now, no atmosphere, no mushroom. The larger the plasma gets, the cooler it becomes, and the less energy it has to make interesting or terrifying things happen. Within seconds of pulling the trigger, the bubble reddens and fades from view. It would be visible from the Earth like a star flickering to life, only to fade out right away. A spark and then nothing. As the cloud of tiny debris reaches far above the surface of the Moon, it's illuminated by the sun for a few minutes, giving it an eerie beauty for anyone left to observe the spectacle. What about the Moon's orbit? It's basically unchanged. Trying to move the Moon with a nuke is like trying to move a truck by blowing on it. Nuclear explosions may be big, but space is bigger. Our mighty explosion just leaves another crater, one among millions. Still, anyone on the Moon will continue to not enjoy themselves. The material that ends up raining back to the Moon is radioactive, and without any natural processes to wash it away or bury it, the surface of the Moon will remain contaminated. Although fortunately, the worst of the radiation will have decayed to a level comparable to natural levels from cosmic rays in about a year. In conclusion, we can say with confidence that while the Moon itself does not care about being nuked, and will barely notice, using the Moon as a nuclear test ground kind of ruins it for everyone trying to spend some time there or to build something useful. So maybe we should just not do that. The beginning of everything, the Big Bang. The idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity, and Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered, a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like the Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seem to suggest that the expansion of the universe is accelerating. But how did this Big Bang work? How can something come from nothing? Let's explore what we know. We can ignore the beginning part for now. First of all, the Big Bang was not an explosion. It was all space, stretching everywhere, all at once. The universe started very, very, very small and quickly expanded to the size of a football. The universe didn't expand into anything, space was just expanding into itself. The universe cannot expand into anything because the universe has no borders. There is, by definition, no outside the universe. The universe is all there is. In this hot, dense environment, energy manifested itself in particles that existed only for the tiniest glimpses of time. From gluons, pairs of quarks were created, which destroyed one another, perhaps after giving off more gluons. These found other short-lived quarks to interact with, forming new quark pairs and gluons again. Matter and energy were not just theoretically equivalent, it was so hot they were practically the same stuff. Somewhere around this time, matter won over antimatter. Today, we're left with almost all matter and nearly no antimatter at all. Somehow, 1,000,000,001 matter particles were formed for every 1,000,000,000 particles of antimatter. Instead of one massive ultimate force in the universe, there were now several refined versions of it acting under different rules. By now, the universe has stretched to 1,000,000,000 kilometers in diameter, which leads to a decrease in temperature. The cycle of quarks being born and converted back to energy suddenly stops. From now on, we work with what we have. Quarks begin forming new particles, hadrons, like protons and neutrons. There are many, many combinations of quarks that can form all sorts of hadrons, but only very few are reasonably stable for any length of time. Please take a moment to appreciate that by now, only 1 second has passed since the beginning of everything. The universe, which has grown to 100 billion kilometers, is now cold enough to allow most of the neutrons to decay into protons and form the first atom, hydrogen. Imagine the universe at this point as an extremely hot soup, 10 billion degrees Celsius, filled with countless particles and energy. Over the next few minutes, things cooled and settled down very fast. Atoms formed out of hadrons and electrons, making for a stable and electrically neutral environment. Some call this period the Dark Age because there were no stars and the hydrogen gas didn't allow visible light to move around. But what's the meaning of visible light anyway, when there's nothing alive yet that could have eyes? When the hydrogen gas clumped together after millions of years and gravity put it under great pressure, stars and galaxies began to form. Their radiation dissolved the stable hydrogen gas into a plasma that still permeates the universe today and allows visible light to pass. Finally, there was light. Okay, but what about the part we didn't talk about? What happened right at the beginning? This part can be defined as the Big Bang. We don't know at all what happened here. At this point, our tools break down. Natural laws stop making sense. Time itself becomes wibbly-wobbly. To understand what happened here, we need a theory that unifies Einstein's relativity and quantum mechanics, something countless scientists are working on right now. But this leaves us with lots of unanswered questions. Were there universes before our own? Is this the first and only universe? What started the Big Bang, or did it just occur naturally based on laws we don't understand yet? We don't know, and maybe we never will. But what we do know is that the universe as we know it started here and gave birth to particles, galaxies, stars, the Earth, and you. Since we ourselves are made of dead stars, we are not separate from the universe. We are part of it. You could even say that we are the universe's way of experiencing itself. So let's keep on experiencing it until there are no more questions to ask. It's hard to get to space. As much as we all wish there were an easy and affordable way to see our planet floating in the dark, right now, the only way is to become an astronaut or a billionaire. But there is a concept that might make it possible while serving as the starting point for the exploration of the universe, the space elevator. How exactly does it work? To understand how a space elevator will get us into space, we must first understand what an orbit is. Being in orbit basically means falling towards something but moving fast enough to miss. If you throw a ball on Earth, it makes an arc through the air and then hits the ground. In space, gravity makes you move much the same way, but if you move sideways fast enough, the curvature of the Earth makes the ground fall away beneath you as fast as gravity pulls you towards it. So to enter Earth's orbit, rockets have to go up and sideways fast. By contrast, a space elevator taps into energy from the Earth's rotation to get the cargo going fast. Imagine a child spinning a toy on a rope with an ant on the child's hand. As the ant climbs out along the rope, it starts to move faster and faster as it ascends. Compared to rockets, with cargo launched on an elevator, you only need to provide the energy to go up. Fast sideways movement comes free with the Earth's rotation. But a space elevator would, without a doubt, be the single largest and most expensive structure ever built by humans. So, is it worth it? It all comes down to costs. Rockets burn a huge amount of rocket fuel just to get a small amount of cargo into space. At current prices, it costs about $20,000 to put 1 kilogram of payload into space. That's $1.3 million for the average human, $40 million for your car, billions for an international space station. This immense cost is one of the major limitations of human spaceflight. Even with advancing technology, this cost isn't likely to be comparable with the price of an airline ticket anytime soon. A space elevator would solve this problem. After construction, a space elevator is projected to reduce the cost 100-fold to $200 per kilogram. If an inexpensive space elevator costs $20 billion, then we'll recoup our losses after launching only 1,000 tons, close to the weight of 2 international space stations. So what would a space elevator look like in real life? A space elevator has 4 major components: the tether, anchor, counterweight, and climber. The elevator part of the space elevator is the tether and the climber. It extends from the surface of the Earth to space. The climber is like a conventional elevator carriage, a chamber that works its way up and down the tether. At the base would be an anchor, pinning the tether to the Earth, along with a port for climbers. At the top is the counterweight, which holds up the tether. The tether is held tight like a rope and supported from above by the tension from the counterweight, located higher than 36,000 kilometers above the Earth's surface. At the counterweight could be a space station, a launching point for all missions from the spaceport elevator. But can we actually build one? It's hard to say. The biggest challenge is the tether. It needs to be light, affordable, and more stable than any material we can produce right now. There are promising materials like graphene and diamond nanothreads, but even they may not be strong enough. And aside from being incredibly strong, the tether would also have to withstand atmospheric corrosion, radiation, and micrometeorite and debris impacts. Additionally, it takes several days to climb the elevator. How do we power the climber? It requires a lot of energy to go up. Do we need a nuclear reactor on our elevator carriage? Or do we beam it power from the ground with a super-powered laser? And where do we get the raw materials for a 36,000-kilometer long tether? Do we make it on Earth and launch it into space, or do we make it in space and lower it down to the Earth? Could asteroid mining be the answer? Put simply, there are still some major technological hurdles to overcome. And a space elevator is not without risk. Should the tether break, it would collapse in spectacular style. If it breaks near the anchor, the force exerted by the counterweight will cause the entire elevator to rise up, ascending into space. Should it break near the counterweight, the tether will fall, wrapping around the world and whipping the end off. The resulting debris in orbit could pose serious problems to future spaceflight. If we build a space elevator on Earth, we have to do it right the first time. For these reasons, some experts have proposed first building a space elevator on the Moon. The Moon's gravity is much weaker than the Earth's, so a flimsier but existent material like Kevlar could serve as a tether. Even with all these challenges, the payoff of having a working space elevator would be immense. It might be the first step to truly becoming a spacefaring civilization. Maybe we will never build a space elevator, but in trying to do so, we might learn an awful lot. And when it comes to the exploration of the universe, there can't be too many dreams of a glorious future. Getting to space is hard. Right now, it's like going up a mountain on a unicycle with a backpack full of explosives. Incredibly slow, you can't transport a lot of stuff, and you might die. A rocket needs to reach a velocity of about 40,000 kilometers an hour to escape from Earth. To get to that speed, rockets are mostly containers for fuel with a tiny tip of payload. This is bad if you want to go to other planets because you need a lot of heavy stuff if you want to survive and maybe even come back. So is there a way to get to space with less fuel and more payload? A nice thing that solved most of our transport problems on Earth is what you call infrastructure. Whether it's roads for cars, ports for ships, or rails for trains, we've made it easier to get to places. We can apply the same solution to space travel. Space infrastructure will make getting into orbit and out to the Moon, Mars, and beyond easier and cheaper. Great, but what exactly is space infrastructure? Unlike an Earth space elevator, which is currently science fiction, there is a simple yet promising technology that does not require new science, magic materials, or huge investments, and that has been tested successfully in orbit already. A cable and a weight, known as a tether. The concept is so simple, it's surprising. What if we put tethers, hundreds or thousands of kilometers long, into space and had spacecraft use them as ladders to climb to higher altitudes and gain speed? This concept is known as the skyhook. It works even better if we make it spin. A counterweight holds a long cable in place while it rotates around a circle. A rotating tether slows down its tip relative to the ground at the bottom and speeds it up at the top like a catapult. This means that you can transfer energy from the tether and get a massive boost when released, more or less for free, equal to twice the tether's rotation velocity. Specialized fibers already exist that can survive the extraordinary stresses a skyhook would be faced with. To protect against cuts and collisions from debris and meteorites, we can thread our tether into a web of redundant fibers. Since our skyhook would pass over the same spot many times a day, this would allow small, reusable shuttles to catch up with it. Of course, it's not that easy. At its lowest point, the tether's tip is dashing through the atmosphere at around 12,000 kilometers per hour. Because of Earth's atmosphere, we can't lower the skyhook too much or it will get too hot from air friction. So it will dip to a height of 80 to 150 kilometers and no lower. To match this, we'll need specialized spacecraft that can get to the tether. While this isn't exactly easy, it's still much cheaper than getting a big tin can filled with rocket fuel to go 40,000 kilometers an hour. Catching the tip will be a challenge too. There's only a short time window of 60 to 90 seconds to find a tiny thing in the sky moving at Mach 12. To make this easier, the tip could have a sort of fishing line, a kilometer long, with a navigation drone that helps the spacecraft connect. Another challenge is keeping our skyhook in orbit. As more and more ships latch onto it and pull themselves up, they use up the momentum that keeps it in place. If we don't do anything, it will slow down and crash into the atmosphere. And here, we can cheat the universe a bit. The skyhook is a battery of orbital energy. It's possible to balance the payloads coming in and being sent off. Arriving ships bringing humans and materials home to Earth add energy to the tether, which it can give to other ships departing into space. This way, the tether doesn't lose any energy. The more we use it, the cheaper it gets. If we're still losing energy with each boost, we can recover it with small electric or chemical engines that regularly correct the tether's position. A set of tethers, one around Earth and one around Mars, could make trips between the planets fast, straightforward, and low cost compared to rockets. The Earth tether would sit in low Earth orbit to grab people and payloads and fling them off to Mars. The Mars tether catches them and slows them down for a landing on the surface. In the opposite direction, the tether could pick up a vehicle traveling through Mars's thin atmosphere at only about 1,000 kilometers an hour, not much faster than our airliners on Earth, and fling it back to Earth to be caught and lowered down. The tethers could shorten trips between both planets from 9 months down to 5 or even 3, and reduce the scale of the rockets required by between 84 and 96%. Even better, people may be able to travel in relative luxury as we could afford to invest in passenger comfort. Tether travel would be first-class seats to Mars. Together, tethers around Earth and Mars could provide the rapid and cost-efficient transportation backbone that would make space travel affordable. But let's go further. Starting from low Mars orbit, a tether could boost ships to the asteroid belt. The first craft sent to a new asteroid would need rockets to slow down at its destination. Subsequent arrivals might find a tether waiting to catch them and send them back for free. Getting to asteroids cheaply is a major factor in opening up the resources of the solar system. Precious metals and valuable minerals could be delivered to Mars just weeks after they were cut out of their asteroid. They would be the perfect building blocks for our interplanetary civilization. But why stop here? Mars moons are very convenient. No other moons in the solar system orbit that close to their planet. Phobos is so heavy that we don't need to worry about slowing it down, making it the perfect attachment point for super tethers just under 6,000 kilometers long. The lower tip would fly just over the surface of Mars and be very easy to catch. The upper tip can fling ships all the way to Jupiter and Saturn. The same super tether can also bring the inner solar system closer. Venus and Mercury are a single swing away. Unlike Mars, they're bursting with solar energy and are rich in minerals. In the long term, nothing is stopping humanity from constructing a zero-propellant transport network for the terrestrial planets centered on the Martian moons. Tethers are a comparably cheap and sustainable solution to making space travel affordable and the rest of the solar system accessible for exploitation and exploration. Considering that we have the technology to build them today, there's really no good excuse to wait any longer. Parts of the solar system are far away, but they could be very close. What is the largest star in the universe? And why is it that large? And what are stars anyway? Things that would like to be stars. We begin our journey with Earth, not to learn anything, just to get a vague sense of scale. The smallest things that have some star-like properties are large gas giants or sub-brown dwarfs, like Jupiter, the most massive planet in the solar system, 11 times larger and 317 times more massive than Earth, and more or less made of the same stuff as our Sun, just much less of it. The transition towards stars begins with brown dwarfs, failed stars that are a huge disappointment to their mums. They have between 13 and 90 times the mass of Jupiter. So even if we took 90 Jupiters and threw them at each other, although fun to watch, it wouldn't be enough to create a star. Interestingly, adding lots of mass to a brown dwarf doesn't make it much bigger, just its insides denser. This increases the pressure in the core enough to make certain nuclear fusion reactions happen slowly and the object glow a little. So brown dwarfs are a sort of glowy gas giant that don't fit into any category very well. But we want to talk about stars, not failed wannabe stars, so let's move on. Main sequence stars. Once large gas balls pass a certain mass threshold, their cores become hot and dense enough to ignite. Hydrogen is fused to helium in their cores, releasing tremendous amounts of energy. Stars that do that are called main sequence stars. The more massive a main sequence star is, the hotter and brighter it burns, and the shorter its life is. Once the hydrogen burning phase is over, stars grow, up to hundreds of thousands of times their original size. But these giant phases only last for a fraction of their lifespan. So we'll be comparing stars at drastically different stages in their lives. This doesn't make them less impressive, but maybe it's good to keep in mind that we'll be comparing babies to adults. Now back to the beginning. The smallest real stars are red dwarfs, about 100 times the mass of Jupiter, barely massive enough to fuse hydrogen to helium. Because they are not very massive, they are small, not very hot, and shine pretty dimly. They are the only stars in the main sequence that don't grow once they die, but sort of fizzle out. Red dwarfs are by far the most abundant type in the universe. Because they burn their fuel very slowly, it lasts them up to 10 trillion years, 1,000 times the current age of the universe. For example, one of the closest stars to Earth is a red dwarf star, Barnard's star, but it shines too dimly to be seen without a telescope. We made a whole video on red dwarfs if you want to learn more. The next stage are stars like our Sun. To say the Sun dominates the solar system is not doing it justice, since it makes up 99.86% of all its mass. It burns far hotter and brighter than red dwarfs, which reduces its lifetime to about 10 billion years. The Sun is 7 times more massive than Barnard's star, but that makes it nearly 300 times brighter with twice its surface temperature. Let's go bigger. Small changes in mass produce enormous changes in a main sequence star's brightness. The brightest star in the night sky, Sirius, is 2 solar masses with a radius 1.7 times that of the Sun, but its surface is nearly 10,000 degrees Celsius, making it shine 25 times brighter. Burning that hot reduces its total lifespan by 4 times to 2.5 billion years. Stars close to 10 times the mass of our Sun have surface temperatures near 25,000 degrees Celsius. Beta Centauri contains 2 of these massive stars, each shining with about 20,000 times the power of the Sun. That's a lot of power coming from something only 13 times larger, but they'll only burn for about 20 million years. Entire generations of these blue stars die in the time it takes the Sun to orbit the galaxy once. So is this the formula? The more massive, the larger the star. The most massive star that we know is R136A1. It has 315 solar masses and is nearly 9 million times brighter than the Sun. And yet, despite its tremendous mass and power, it's barely 30 times the size of the Sun. The star is so extreme and barely held together by gravity that it loses 321,000 billion tons of material through its stellar wind every single second. Stars of this sort are extremely rare because they break the rules of star formation a tiny bit. When supermassive stars are born, they burn extremely hot and bright, and this blows away any extra gas that could make them more massive. So the mass limit for such a star is around 150 times the Sun. Stars like R136A1 are probably formed through the merger of several high-mass stars in dense star-forming regions and burn their core hydrogen in only a few million years. So this means they are rare and short-lived. From here, the trick to going bigger isn't adding more mass. To make the biggest stars, we have to kill them. Red giants. When main sequence stars begin to exhaust the hydrogen in their core, it contracts, making it hotter and denser. This leads to hotter and faster fusion, which pushes back against gravity and makes the outer layers swell in a giant phase. And these stars become truly giant indeed. For example, Gacrux. Only 30% more massive than the Sun, it has swollen to about 84 times its radius. Still, when the Sun enters the last stage of its life, it will swell and become even bigger, 200 times its current radius. In this final phase of its life, it will swallow the inner planets. And if you think that's impressive, let's finally introduce the largest stars in the universe, hypergiants. Hypergiants are the giant phase of the most massive stars in the universe. They have an enormous surface area that can radiate an insane amount of light. Being so large, they're basically blowing themselves apart, as gravity at the surface is too weak to hold on to the hot mass which is lifted away in powerful stellar winds. Pistol Star is 25 solar masses, but 300 times the radius of the Sun, a blue hypergiant aptly named for its energetic blue starlight. It's hard to say exactly how long Pistol Star will live, but probably just a few million years. Even larger than the blue hypergiants are the yellow hypergiants. The most well-studied is Rho Cassiopeia, a star so bright it can be seen with the naked eye, although it's thousands of light years from Earth. At 40 solar masses, this star is around 500 times the radius of the Sun and 500,000 times brighter. If the Earth were as close to Rho Cassiopeia as it is to the Sun, it'd be inside it and you would be very dead. Yellow hypergiants are very rare though, only 15 are known. This means they're likely just a short-lived intermediate state as a star grows or shrinks between other phases of hypergiantness. With red hypergiants, we reach the largest stars known to us, probably the largest stars even possible. So, who's the winner of this insane contest? Well, the truth is, we don't know. Red hypergiants are extremely bright and far away, which means that even tiny uncertainties in our measurements can give us a huge margin of error for their size. Worse still, red hypergiants are solar system-sized behemoths that are blowing themselves apart, which makes them harder to measure. As we do more science and our instruments improve, whatever the largest star is will change. The star that is currently thought to be among the largest we've found is Stephenson 218. It was probably born as a main sequence star a few tens of times the mass of the Sun and has likely lost about half its mass by now. While typical red hypergiants are 1,500 times the size of the Sun, the largest rough estimate places Stephenson 218 at 2,150 solar radii and shining with almost 500,000 times the power of the Sun. By comparison, the Sun seems like a grain of dust. Our brains don't really have a way of grasping this kind of scale. Even at light speed, it would take you 8.7 hours to travel around it once. The fastest plane on Earth would take around 500 years. Dropped on the Sun, it would fill Saturn's orbit. As it evolves, it will probably shed even more mass and shrink down into another hotter hypergiant phase, accumulate heavy elements in its core, before finally exploding in a core collapse supernova, giving its gas back to the galaxy. This gas will then go on to form another generation of stars of all sizes, starting the cycle of birth and death again to light up our universe. Let's make this journey again, but this time without the talking. The universe is big. There are many large things in it. If you want to play a bit more with size stuff, we have good news. We've created our first app, Universe in a Nutshell, together with Tim Urban, the brain behind Wait But Why. You can seamlessly travel from the smallest things in existence, past the coronavirus, human cells and dinosaurs, all the way to the largest stars and galaxies, and marvel at the whole observable universe. You can learn more about each object or simply enjoy the sheer scale of it all. The app is inspired by the Scale of the Universe website by the Huang twins that we spent a lot of time with when it came out years ago, and felt that it was finally time to create a Wait But Why and Kurzgesagt version. You can get it in your app store, there are no in-app purchases and no ads. All future updates are included. And since this is our first app, we'd love to hear your feedback so we can improve it over time. If this sounds good to you, download the Universe in a Nutshell app now and leave us a 5-star review if you want to support it. Kurzgesagt and all the projects we do are mostly funded by viewers like you. So if you like the app, we'll make more digital things in future. Thank you for watching. Casually watching a video on YouTube on a computer more powerful than anything humanity could build a few decades ago. This progress and all the wonderful machines you take for granted are built on a few rare and precious materials with names like terbium, neodymium, or tantalum. Getting these rare materials from the ground into your devices is ugly. The mining industry is responsible for air and water pollution and the destruction of entire landscapes. Dangerous chemicals like cyanide, sulfuric acid, or chlorine are used to extract the resources, harming biodiversity, workers, and locals. And rare resources are also political tools when countries restrict access to them to get their way. But what if we could replace the mining industry on Earth with a clean process that can't harm anyone? Well, we can. All we need to do is look up. Asteroids are millions of trillions of tons of rocks, metals and ice, leftovers from the cloud that became the planet 4.5 billion years ago. They can be as small as a meter or protoplanets the size of entire countries. Most of them are concentrated in the asteroid belt and the Kuiper belt, while hundreds of thousands more do their own thing between the planets. As space travel is becoming more feasible, scientists and economists have begun looking at the resources found in these asteroids. Even relatively small metallic asteroids may contain trillions worth of industrial and precious metals like platinum. And bigger asteroids like 16 Psyche could contain enough iron-nickel to cover the world's metal needs for millions of years. At current market prices, the rare raw materials alone would be worth quadrillions of dollars. Well, not really, but technically. For example, there are more than 20 million tons of gold in the ocean's water, worth roughly 750 trillion US dollars. But filtering out the gold would be so expensive that you'd lose money selling it. Right now, asteroid mining has exactly this problem. It's too expensive to replace mining on Earth. Billions of dollars worth of valuable resources in space are worthless if it costs trillions to get them. What makes it so hard? The principles behind mining an asteroid are simple. The basic idea is to choose an asteroid, move it to a place where it's easy to process, and then take it apart to turn into useful products. Unfortunately, all of this collides with fundamental problems humans have yet to solve. Going to space is expensive. It costs thousands of dollars in rocket fuel for each kilogram just to reach a low Earth orbit. Going further out into deep space costs thousands more. We need cheaper space travel to make asteroid mining profitable. One solution is to switch from classical rockets to electric spaceships. We already use electrical rocket engines for many of the space probes on science missions. In principle, we only need to build bigger ones. While electrical engines are not powerful enough to fly to space, they require only a tiny amount of fuel to go very far once they're in space. This means we don't need to spend a lot of money on fuel only to transport fuel into space. This doesn't solve the whole cost problem, but it makes it easier to start our first mission. Now that we have an electric asteroid mining spaceship, we need to find the right asteroid and get it there. We've already successfully visited asteroids with space probes and even collected samples. Still, to make it easier and cheaper, our first targets will probably be near-Earth asteroids. Asteroids that orbit, well, near Earth. After a few months of travel, our spaceship finally arrives at our asteroid. Weirdly formed, littered with small impact craters, it hasn't changed much for billions of years. The first thing that needs to be done is to secure the asteroid and stop it from spinning. There are multiple ways to do this, like vaporizing material with a laser or stopping the rotation with thrusters. Once we have a stable asteroid, we need to wait. Orbital mechanics are complicated, but if you push something in the right direction at exactly the right moment, you can move very big things with very little force. So, we wait for exactly the right moment. Our ship fires its thrusters and nudges the asteroid into a trajectory that takes it near our moon. The moon is useful because we can borrow its gravitational pull to put the asteroid in a stable orbit around Earth, which saves even more fuel. Again, the trip takes months. But all the time since our ship was launched has not been wasted. The first space mining and processing equipment has been installed in orbit and is now carefully moving towards the asteroid. The processor works very differently than on Earth. Giant mirrors focus sunlight and heat up asteroid rock to boil out the gases. Grinders break up the dried rocks into gravel and dust, and centrifuges separate dense from light elements. Even if we only extract 0.01% of the asteroid's mass in precious metals, this is still several times more than you'd get from the same amount of ore on the ground. But what now? How do we get our precious metals safely back to ground? There are a few ways, like loading it into reusable rockets that return to Earth from space. Or if our processor contains 3D printers, we can print a faster and cheaper delivery system. Heat-shielded capsules filled with gas bubbles. These can just be dropped into the oceans where ships tow them away. This could be the starting point of humanity's first real steps towards colonizing the solar system. As our infrastructure and experience grows, our missions get more and more sophisticated. Parts and fuel produced on asteroids don't have to be launched from Earth at all. The first mining operation makes the second one easier, and so on. While the space industry grows and precious materials become cheaper, eventually we could stop mining on Earth. Even the idea of toxic mining down here might become something weird and anachronistic, like having an open fire in your living room. Landscapes ravaged by pollution will heal, while the technological wonders we're used to get cheaper and less toxic to make. None of this is science fiction. We don't need fancy materials or new physics to make asteroid mining happen. We could start building this future today. All we need is an initial push. Black holes are the largest collections of pure, violent energy in the universe. If you come too close, they'll devour you and add your energy to their collection. And so the energy is lost to us forever. Or is it? It turns out there's a universe cheat code. A way of powering civilizations until the very death of everything, or of constructing the largest bomb in the universe. But how? Didn't we learn that all energy is trapped forever in black holes, even light? This is true. Everything you think you know about the weirdest thing in the universe is about to get weirder for one simple reason. Black holes are spinning. Why black holes spin? When really massive stars die, their cores collapse under their own gravity into black holes. This means something very big becomes very tiny, like the tiniest anything can be in this universe. But stars are rotating, and a fundamental property of our universe is that things that are spinning don't want to stop spinning. We call this angular momentum. And this angular momentum can't go away. A big thing that spins and becomes smaller spins faster. So, as the core of a star collapses, its momentum makes it spin faster and faster and faster until it collapses into a black hole. And the black hole keeps on spinning, inconceivably fast. Some of them spin millions of times a second. Why spinning black holes are special? Just like non-spinning black holes, spinning black holes have an event horizon and a singularity at their core where all of their mass is concentrated. The singularity is usually described as a single, infinitely small point with no surface area. But points can't rotate, so a rotating singularity can't be a point. Instead, it's a ringularity. A ringularity is a ring with a thickness of 0 and no surface, spinning extremely fast, containing all the mass of the black hole. The black hole is spinning so fast that it morphs space and time itself. It literally drags space with it, such is its power. This creates a new and super weird region of space-time, the ergosphere, which envelops the black hole. If space and time are completely broken inside the event horizon, then they're only half broken inside the ergosphere. Inside the ergosphere, nothing makes sense. It's possible to enter it and then leave it again, but it's probably not a great experience. You can imagine it like this. Falling into a static black hole is like sliding down a hole. Being inside the ergosphere of a spinning black hole is like spiraling down a deadly drain. The black hole transfers its own kinetic energy in the form of rotation to everything that enters the ergosphere. The ringularity makes you dance whether you want to or not. You need to move faster than the speed of light just to stand still here, which is impossible. But here's our cheat code. We can steal this energy. And there's a lot of energy to steal. How to steal energy from a monster. Take the supermassive black hole at the center of the Milky Way. We could steal as much energy from it as every single star in the Milky Way emits in 1 billion years combined. The easiest way to steal this energy is, oddly enough, to drop something into the black hole. We've seen that the ringularity forces energy on us when we enter the ergosphere, which is a lot like being in a whirlpool with space-time rushing around and around. If you're clever, you can use the water to your advantage and swim faster than before. In practice, this means sending a rocket into the ergosphere and making a trade with the black hole. We give it some mass energy, and it gives us some of its rotational energy. But it's not a fair trade. We get the better deal. Normally, if you fire a rocket, you exchange chemical energy for kinetic energy. This is like pushing yourself forward in a swimming pool. But if you fire a rocket inside the ergosphere, it's like pushing yourself forward in a wave pool. The rotational energy of the waves gives you a much stronger boost than you could get just by pushing yourself. The boost from the rotation of the black hole is so big that you leave the ergosphere with much more energy than you entered it. The black hole gives a tiny amount of its rotational energy to you and slows down a little. Obviously, this requires a lot of food. Fortunately, black holes aren't picky eaters. An advanced future civilization would probably harvest asteroids to drop them into the black hole when they needed an energy boost. But there's an even better way to get energy from a black hole, and oddly enough, it builds the biggest bomb any living thing could ever hope to build. The black hole bomb. We only need two things to build a black hole bomb: a fast spinning black hole and a big mirror. The mirror has to completely envelop the black hole, which is similar to a Dyson sphere, a megastructure that harvests the energy of an entire star. Although our mirror would be easier to build, mirrors are simpler and black holes are much more compact than stars. If we made the mirror 10 centimeters thick, the metal of a big asteroid would probably be enough material for a black hole with the mass of our Sun. Once our mirror is in place, we only need to open a window and shoot electromagnetic waves at the black hole. You can imagine what happens next by imagining tossing a ball at a wall and it coming back faster than a bullet. The waves hit the black hole at light speed. A small proportion of the waves falls past the event horizon to disappear forever. But a much larger amount sloshes through the ergosphere, where the black hole forces some of its rotational energy on them and amplifies them. They now begin super radiant scattering, which are fancy science words meaning bouncing around between mirror and black hole and getting stronger. Every time they go around, they are getting exponentially stronger. By opening some windows in the mirror, we can extract the energy from the waves as fast as they grow, which we could use, in theory, to create what would be, for all practical purposes, an endless source of energy for trillions of years. Or we could blow it up. If the waves are not released, they will continue to get stronger and stronger and take more and more energy from the black hole until the mirror shatters. A supermassive black hole would release as much energy as a supernova, making the bomb the largest explosion any living being could ever create. The last home in a dying universe. The beauty of the black hole bomb, the Penrose process, and the super radiant scattering is that they are not science fiction. In the far, far future, this might be the only way to survive in our dying universe. After all the red dwarfs have cooled down and all the white dwarfs transformed into black dwarfs, the universe will turn dark forever. Rotating black holes might be the only sources of energy in the entire universe that life could harvest. If so, the last living being in existence might one day end its life around a black hole, which is equally chilling and uplifting. It turns out that even without any light, there are places we can go. Leaving Earth to find new homes in space is an old dream of humanity and will sooner or later be necessary for our survival. The planet that gets the most attention is Mars, a small, toxic and energy-poor planet that just about seems good enough for a colony of depressed humans huddled in underground cities. But what if we think bigger? What if we take Venus, one of the most hostile and deadly places in the solar system, and turn it into a colony? Not by building lofty cloud cities, but by creating a proper second Earth. It might be easier than you think. Venus is by far the hottest planet in the solar system, with a surface temperature of 460 degrees Celsius, hot enough to melt lead. This heat is due to the most extreme greenhouse effect in the solar system. CO2 is great at trapping heat. Even a rise from 0.03% to 0.04% in Earth's atmosphere is heating up our planet right now. Venus's atmosphere is 97% CO2. Also, Venus's atmosphere is 93 times denser than Earth's. Standing on Venus's surface would feel like taking a dive about 900 meters deep into the ocean. The pressure would kill you instantly. It's a truly horrible place, so why should we even bother? First and foremost, Venus is almost as big as Earth and has 90% of its surface gravity. Surface gravity is a big problem when colonizing the solar system because it's very likely that long stays in low-gravity places will have negative health effects. Venus's size means it could be the second largest habitat in the solar system. A new home for billions of humans and trillions of animals, with oceans, lush forests, and a beautiful blue sky. A properly terraformed Venus may be the most pleasant place to live outside of Earth. While we can't exactly terraform Venus today, a slightly more ambitious future version of us could take this project on. It will take a few generations to complete and be a huge challenge like building the Great Pyramids was for our ancestors. But then, it's not like humans have never started projects that took more than a lifetime to complete. Okay, let's do it. Before anything else, we need to cool Venus down and remove the gas that makes up the extremely heavy atmosphere. As mentioned, there's a lot of it. Around 465 million billion tons. How do we do that? There are a few options. We could create giant solar collectors powering a huge array of laser beams that heat up the atmosphere so much that it's blasted into space. Although we would need thousands of times the entire power generating capacity of humanity, and it would still take thousands of years to remove the atmosphere. Another way is to sequester the atmosphere, binding the CO2 in different compounds through chemical reactions. We could mine elements like calcium or magnesium on Mercury and shoot them at Venus via mass driver systems, electric rails that make rockets unnecessary on smaller planets. The metals would combine to bind the CO2 into different carbonates basically forever. But the scale makes the whole thing impractical. We would need several 100 billion tons of material to sequester the CO2 this way. Seems like a waste of material and might take too long. An equally ridiculous idea that could actually work is to put Venus in the shade, literally, by constructing a huge mirror to blot out the sun to just freeze the atmosphere. The mirror doesn't need to be complex or massive, just a very thin foil with a little structural support. Building such a large flat surface so close to the sun will turn it effectively into a solar sail and push it out of position. So instead of one giant circular object, our mirror will consist of many different pieces. Annular slats of angled mirrors can reflect sunlight from one set of mirrors to the next. Mirrors would be angled, reflecting light from one to another until the light is redirected to the back, balancing the force on the front and holding them in position. After a few years of getting the infrastructure in place, things start slowly and then escalate. For the first few decades, the atmosphere slowly cools down but stays dense and deadly. Until after some 60 years, it reaches the critical temperature of 31 degrees Celsius. Suddenly, the Great Flood begins on Venus as CO2 turns to liquid at this pressure and begins to rain down. A constant global rainstorm of unbelievable proportions lasting 30 years. The pressure and temperature suddenly begin to drop in unison. For almost a century, puddles turn into lakes and oceans. The surface temperature is now minus 56 degrees Celsius and the pressure has dropped to only 7 times the pressure on Earth. Finally, at a really unpleasant minus 81 degrees Celsius, the CO2 oceans begin to freeze and the rain turns into snow. This leaves us with a frozen Venus covered in oceans as hard as rock and gigantic CO2 glaciers. What remains of the atmosphere is mostly nitrogen at about 3 times Earth's surface pressure. If you don't mind freezing and suffocating, you can now take a stroll over Venus's surface. But the frozen CO2 remains a bit of a problem. At some point, we want to warm up the planet, but if we do, the CO2 ice will melt and fill up the atmosphere again. So we need some way to keep it from doing that. One is to simply cover it all with cheap plastic insulation and cover it up with ground-up Venus rock or water oceans. Although some planetary scientists will be very stressed out about us building a new planet containing a potential time bomb like that. A few unfortunately timed volcanoes could melt a lot of CO2 at once and ruin everything. Another obvious solution is to shoot it all out into space and collect it into a small moon for storage and future use. We can make this more efficient by using mass drivers instead of rockets, but moving all that mass will still be a pretty intense challenge that will take some time to solve. Whatever we end up doing with the atmosphere, to move forward we need water, which we could get from ice moons. Europa, a moon of Jupiter, has twice as much water as Earth's oceans. Now, catching a moon and transporting it through the solar system is not exactly easy. So instead, it might be easier to cut chunks of ice off Europa with an army of construction drones and shoot them at Venus using more of those mass drivers. Space tethers could save us a lot of effort and energy here. We made a whole video explaining how they work, but in a nutshell, they are slings that can take a payload on both ends. On Europa, they do most of the work needed to catapult our ice to Venus. The ice hits the Venus tethers, which gently drop it into the atmosphere, where it falls down as snow. In exchange, the Venus tethers get to catch CO2 ice shot up from below and accelerate it into orbit. We can remove excess nitrogen using this same method to further lower our atmospheric pressure. After a few decades or centuries, Venus would be covered by a nice, shallow, frozen ocean a few hundred meters deep. It would look extremely different from today. A few continents and countless islands have formed. This is beginning to look a bit like our planet. Now the last and most magnificent phase of terraforming begins, making the atmosphere breathable and adding life. First, we need light though, and we need to heat the planet up again. A Venus day is 2,802 hours long, more than 116 Earth days. So if we just remove our giant mirror, we would grill half of our planet. Even without the massive atmosphere, temperatures would reach unbearable levels. The simplest way to create a day-night cycle and let some energy in again is with another set of mirrors to illuminate our continents and melt our water oceans, which would let us completely control how much energy we get and where it goes. The atmosphere is now mostly made up of nitrogen and basically devoid of oxygen. So the first inhabitants will likely be trillions and trillions of cyanobacteria, which can get photosynthesizing and release oxygen. We know that they can quickly turn around the atmosphere of a planet because billions of years ago they were probably responsible for turning the toxic atmosphere of our young Earth into an atmosphere with enough oxygen for more complex animal life. But not only that, cyanobacteria can fix nitrogen from the atmosphere and turn it into nutrients that can be used by living beings. This way, they will essentially fertilize our dead ocean water and prepare it for more complex organisms. On land, our colonists need to grind down some of the former Venusian surface to make soil for nitrogen-fixing plants to grow on. Eventually, billions of trees would spread, creating large forests covering massive parts of the continents. Venus would turn green. To speed things up, CO2 would be strategically released to supply the plants and cyanobacteria. Areas already covered with plants could get extra daylight from our orbital mirrors, so the plants would be active for most of each day. Maybe we won't have to do this with the same plants and animals we know today. As genetic engineering matures and our understanding of genetics and the machinery of life expands, we might just engineer life as we need it. All in all, it would take several thousand years to make the atmosphere breathable by humans. In the meantime, you could stroll around with nothing more than regular clothes and an oxygen mask. Settlers would enjoy a vast new planet filled with resources and bathed in sunlight. They might think of new ways to use the vast amounts of carbon dioxide ice and nitrogen orbiting in space above. Industrial processes, rocket fuel, or even boosting the terraforming of another planet like tiny Mars. Venus is fully terraformed. Animals roam through vast ecosystems. Cities are being constructed. Billions of settlers and their descendants make this world their home. They will see images of the past, how Venus was once the most hostile planet around, how it took hundreds of years to freeze hell and to ship in the oceans, and another few thousand years to make it possible to breathe freely. They will barely be able to believe it. Okay, maybe it's not that easy to terraform Venus, and a lot of things must go right for this future to become reality. But it is possible, and with technology that is within the reach of a motivated and slightly more advanced humanity that wants to venture into space. The only thing that's stopping it is our imagination, and that at least is a problem that's easy to overcome. Humans dream about leaving Earth and traveling through the galaxy, but we were born too early to be part of it. Or were we? The reality is, we could begin our dream by building a moon base today. We actually do have the technology, and current estimates from NASA and the private sector say it could be done for $20 to $40 billion spread out over about a decade. The price is comparable to the International Space Station or the budget surplus of Germany in 2017. Not that big an investment, really. The payoff would be immeasurable. The moon is a sandbox to develop new technologies and exploit unlimited resources. It would start a new space race and lay the foundation for us to spread out into the solar system and beyond. It would create a vast array of new technologies to benefit us on Earth, and we would all be part of it. So why aren't we doing it? Well, sadly, it's hard to get governments interested in long-term investments in the future of humanity. Let's imagine just doing it. If we start today, how would we build a moon base? Throughout history, colonization happened in phases. In the first phase of the age of exploration of the New World, for example, European monarchs funded expeditions to chart and discover and to stake their claims. They planted a flag and set up a camp, but they didn't stay. In the second phase, small missions set up outposts and settlements were founded, which were still very dependent on their home countries for supplies. Some failed, but others survived and established a permanent presence. Only then, in the third phase, did a true colony form to which tradesmen and laborers could emigrate, creating new wealth and opportunities for themselves and their families, sending extreme wealth back to their countries of origin. When we colonize the moon, we'll go through the same three phases, this time without murdering billions of innocent people in the process. The moon is not a welcoming place for living things. A moon day lasts 29 Earth days, with a difference of nearly 300 degrees Celsius between sunlight and shade. There's no atmosphere to shield us from meteorites, big and small, or cosmic radiation. Worse still, the lunar surface is covered in a layer of nasty, jagged dust. The moon is hard, but we're good at doing hard things. In the first phase of lunar colonization, our explorers proved it can be done, that a new world can be reached. This phase started 60 years ago with the Apollo missions. Since then, satellites like the American Lunar Reconnaissance Orbiter have mapped the moon, while rovers like the Chinese U2 have studied the composition of the lunar surface, looking for water ice and metals. Phase 1 is more or less complete. We know what we need to know to enter Phase 2. In the second phase, astronauts will build the first moon base, and this could begin today. The first small moon base could be completed in a decade. The first nation that establishes this base will be akin to the First Nations building outposts in the New World 500 years ago. It's expensive to send rockets to the moon, so we will send as little as possible. The base will be light, little more than inflatable habitats for crews of no more than 12, and will be deployed somewhere with natural shelter. Options include caves, like underground lava tube tunnels, or craters near the poles, where the days are 6 months long. These astronauts will not stay long. The habitat is likely to be abandoned between missions, as solar panels cannot generate electricity during the lunar night. But they'll do the groundwork to enable humans to stay permanently. Our first crew will consist of scientists and engineers who will study the composition of the moon and whose experiments will explore ways of using the available lunar material, say purifying lunar ice and turning it into water for human use. And water is important for far more than drinking. They can use it to experiment with growing plants for food. Hydrogen fuel cells will store power through the long night, extending astronaut stays. And most importantly, it can be split into hydrogen and oxygen, rocket fuel. By harvesting water from the moon and putting it into orbit, the moon base will supply an orbital depot where scientific missions to Mars and the outer solar system can refuel. Compared to the Earth, it's much easier and cheaper to get things off the moon into orbit. Colonizing Mars may mean starting from the moon. But this isn't a true colony, not yet. The base will be abandoned if funding stops. If we want our base to grow into the third phase, into a true colony, it must become self-sufficient, supporting itself via exports to Earth. Now, private contractors arrive, looking to get rich off lunar resources and support services. If it's cheaper to produce rocket fuel in space, what else can they get rich on? They could extract precious metals, abundant in impact craters, and other raw materials from the lunar regolith. One promising possibility is the mining of helium-3, an isotope that could one day be used in nuclear fusion reactors, something the Chinese lunar exploration program is currently looking into. Future colonists may export helium-3 back to Earth, providing us with cheap and clean fusion energy. Asteroids could be pulled into the Moon's orbit and mined. With commercial exports to Earth, the colony is fully in its third phase, self-sufficient and economically productive. Our base will begin using lunar material in its construction projects if it's to continue growing. Fortunately, lunar soil has all the necessary ingredients to make concrete. Robotic mining rigs can sift the lunar dust for organic molecules and could be used to build huge structures way too massive to be brought from Earth, while advances in 3D printing will make it possible to produce almost everything else the crews need. It's hard to say when exactly the colony becomes self-sustaining. Growth is gradual, experiments are replaced by industry, and the population steadily reaches the hundreds, encompassing more than just scientists. Engineers, pilots, and contractors representing countries and corporations will be present. Two of these people will make a breakthrough, not scientific, but social. They will have the first extraterrestrial child. Throughout history, the birth of the first child was celebrated as a moment where the seed of a colony finally and irreversibly took root. Here, it means that the Moon is not just a place for scientists and engineers to work, it's a place for people to live, to raise a family. Once this transition happens, the colony grows rapidly, building more habitats and schools and farms and all the things needed to support the growing population. As our colony grows, all kinds of new technologies will be invented to sustain it. They might develop crops that efficiently recycle carbon dioxide or that grow with very little water. They might find ways to recycle and reuse 100% of their waste, technologies that are extremely valuable for Earth. They could even build the first space elevator in the solar system. With a space elevator, spacecraft, astronauts, and raw materials could be brought back and forth from lunar orbit without needing to use rockets at all. The Moon may become a hub for economic activity on a scale that's hard to imagine right now. It's hard to say who will own the colony at this point. Will the first person born on the Moon take the national identity of their parents, or will a new generation meld together into a new lunar society? And when existing treaties that bar any nation from owning the Moon are inevitably rewritten, will the colonists be given a say? Will they declare independence from the Earth? However it happens, the Moon is a perfect sandbox to learn how to colonize the solar system, the perfect project to unify nations, and the only way to guarantee our survival as a species should something tragic happen on Earth. If we ever want to colonize the Milky Way, we'll have to start somewhere. So why not start there? Why not start now? Absolutely everything you think about yourself and the universe could be an illusion. As far as you know, you are real and exist in a universe that was born 14 billion years ago and that gave rise to galaxies, stars, the Earth, and finally you. Except, maybe not. You may actually not exist for real, but be the dream of a dead universe. You and everything you think exists. Crazy as it sounds, this may be an unavoidable consequence of our best scientific theories about the universe. Okay, this is a bit much. Let's start at the beginning. We need to understand three concepts for this idea to make sense. 1. The arrow of time. What distinguishes the past from the future? Put a drop of red ink into a glass of water, and you see the ink spread until it fills the container, but never the opposite. Colored water where ink spontaneously concentrates and becomes a drop at the surface again. Time always seems to flow in the direction in which the ink spreads. But if you take a microscope, all you will see will be a swarm of molecules colliding at random. There are no rules, no forwards and backwards. Every individual motion that happens can occur in reverse. But we perceive a sort of arrow of time that makes things happen in one direction. how does this phenomenon occur? Well, this arrow of time is not actually fundamental, but a matter of probability. When ink molecules spread to fill a glass, there are many different slots of space they can occupy, and therefore many different possibilities to combine them. And just like your chances of winning the lottery grow the more tickets you have, the probability that ink molecules will end up filling the glass is much higher than the probability that they'll concentrate in just one spot. So it's not that the ink forming a drop again is forbidden by the laws of physics, it's just extremely unlikely. To see it, you'd have to wait about 10 to the power of 100 sextillion years, a 1 followed by 100 sextillion zeros. If you had this much time to spare, eventually, by pure random chance, you'd see a red blob form again. Actually, with enough time, you could see any shape forming, like, for example, a small, red, soggy brain. Okay, let's move on to idea 2. 2. The far future of the universe. Our universe was born 14 billion years ago in the Big Bang. It expanded and evolved to give rise to the myriads of galaxies and things. In other words, the universe is kind of a glass of water with a lot of ink doing stuff. It has an arrow of time. But the universe is not a static glass, it seems to be getting bigger at an ever-increasing speed because of dark energy. Basically, everything in it is getting more and more diluted. In about 100 trillion years, the last star will die. Then, few interesting things will happen for the next few decillions, vantillions, and googles of years. Eventually, the universe will be a dark place fully dominated by dark energy, a rapidly expanding ball of pure space almost devoid of matter. You might think that this would lead to the ultimate death of everything, but dark energy has one last surprise for you. In a universe dominated by dark energy, space expands so dramatically that it creates a cosmic horizon around you, a border beyond which nothing will ever be able to reach you, not even light. So for every practical purpose, the universe has become a glass of finite size about 36 billion light-years wide, surrounded by an impassable cosmic horizon. Such a universe glass is basically a giant black hole turned inside out. We know that due to quantum effects, all black holes emit a tiny amount of particles, a phenomenon known as Hawking radiation. And so does our inside-out black hole. In the end, this radiation will fill the universe glass with particles again. At this point, so far in the future that giving you a number has no more meaning, we've reached the true final state. The universe has now become a closed box full of particles at an extremely low but finite temperature. And since they have a temperature, they undergo random motions. Or in other words, a glass filled with water and ink and an infinite amount of time ahead. Things are about to become interesting again. 3. Typing monkeys and fake universes. Eternity is a long, long time. So now, even the most extremely unlikely things can happen. The fluctuating particles are bumping into each other over and over and over again, creating every combination of particles that's possible. They're like a monkey typing at random on a typewriter. Almost all of the time it types gibberish. But with enough time, eventually it will write the first acts of Hamlet. And with even more time, the complete works of Eminem. If ink in our universe glass generates any random arrangements of particles, what could they be? Well, a spontaneous fluctuation could give rise to a planet, or to a galaxy, or even to a lot of them. So maybe our universe has already ended, and all we see around us is a pop-up universe. Not a universe that evolved from a Big Bang, but one that fluctuated into existence by pure chance. And that, like the drop of ink, will only exist for a while before dissolving again. Being random, pop-up universes could be similar to ours but with funny glitches. In some of these universes, dinosaurs are riding snails. In another, stars are made of blueberries. In another, you're wearing a funny hat. Scientists in such universes wouldn't understand those glitches, so maybe the greatest mysteries of physics are just nonsense bugs of our pop-up universe. But not all possible fluctuations of our dead universe have the same probability of occurring. Smaller fluctuations are much more probable than bigger ones. A planet is more likely than a galaxy. But you know what's even way more likely? A human brain. Are you actually just a brain? You think, therefore you exist. But what else do you truly know? In the end, your brain is just interpreting signals from your senses and creating a world that you experience. So technically, you could be just your brain that thinks the world is real. And if we follow the logic of the ink in the universe glass, in particular, you could be a disembodied brain that, just by chance, emerged in a dead universe with your complete set of knowledge and memories. This is a pretty bizarre idea, but if we do the maths, it's kind of pretty solid. Let's compare the number of brains inside bodies in a living universe with the number of naked brains in a dead universe. Let's go really big and imagine that a total of 100 quadrillion humans will live around Earth, and that the same amount of people will live around every star in the universe. If we add this together, we get about 10 to the power of 41 brains inside bodies that will exist. However, in a dead universe that has had enough time to explore all possible fluctuations and that will exist forever, the number of naked brains that would emerge is, well, infinite. So the probability that you're a floating brain is not only vastly larger than the probability that you're a real human, it's so inconceivably larger that we can't even meaningfully quantify the difference. How do you compare a number to infinity? So, are you a floating brain that exists for one moment in time, then basically forever passes, and then you exist for another moment in time? Maybe not even in that order. Maybe your life happens backwards and you just don't notice. Maybe you've lived trillions of times already. Are you the dream of a dead universe? Really? Like, really? Well, probably not. First of all, there are a few loopholes. For example, dark energy could behave completely differently from what we think today and lead us to another future. Or maybe our dead universe will be too motionless to allow the creation of brains, even with infinite time. Or maybe the universe will end up dying in another way. Our understanding of the cosmos doesn't have a solid enough foundation for anyone to worry if they're real or not. Loopholes aside, if you were a fluctuating brain, all the laws of physics stored in your brain would have originated at random and shouldn't bear any relation to the real world. But we just used those laws to prove that you're a floating brain. So even if you believe that you are a floating brain, you'd have to admit that you have no good reason to believe that you are actually a floating brain. Okay, so this hallucinatory trip might teach us something about our theories about the universe. But in the end, it's just a really weird exercise in what you can do with physics. An exercise of what brains in bodies are able to think about. So don't worry, you're not a dream of the dead universe. Probably. Are you alone in the universe? Or are you connected to anything? First of all, you're part of a group of mammals that's still very young, but we can make YouTube videos already and build large hadron colliders. We've also split the atom and invented Pokemon. We stem from an ancient life form that began living about 3.5 billion years ago. We feel like we're in control of this planet, but we aren't really. One little asteroid or one creative virus is really all it would take to kill us off for good. Humanity credits itself with being able to destroy the planet, but even with all our nuclear toys, we would probably just cause a huge mass extinction at best. Maybe we could kill 90% of everything living on this planet. Big deal. A few million years later, life would be back everywhere. Most microscopic life and life below the surface wouldn't even be disturbed that much probably. On a geological timescale, our impact on Earth is kind of laughable. We're actually not that powerful. We live on this tiny wet rock that speeds through space following a massive ball of burning plasma. One day, this ball of plasma will stop burning and most likely kill us in the process. If we survive the death of the Sun and colonize the galaxy, theoretically, we could survive until the last star in the universe goes out. After that, life becomes pretty impossible. Okay, so everything has an end. Where does this leave you as an individual? At one point in your life, for about half an hour, you were only one single cell inside your mother's womb, a creature just 0.1 millimeters in diameter. Today, you consist of about 50 trillion cells. 50 trillion incredibly complex little biological machines that are much bigger and more complex than the average bacteria. They operate by the laws of physics and chemistry and use micro-machines to build proteins, make energy usable, devour food, transport resources, transmit information, or reproduce. They communicate, duplicate, commit suicide, fight off intruders, and fulfill super specialized duties for the greater good of keeping you alive, so you can have babies. But where is the you part in this if you're made of trillions of little things? The basic information for you is stored in the DNA. a molecule that encodes the genetic instructions used in the development and functioning of all known living things. If you were to unravel it, it would be 2 meters long. If you combined all the little DNA strings in all your cells, you'd get a string so long that it would stretch to Pluto and back to Earth. That's pretty long. And your DNA is a direct connection to your very first ancestor. Take a second to think about this. In every cell of your body, there's a little string of stuff that's been there in various forms for 3.4 billion years. It evolved, it mutated, it duplicated trillions of times, but it directly connects you to the first living being on this planet. We could say you touched every living being that came before you with your DNA. But you are more than your DNA. Your body is made of 7 octillion atoms. That's 7 billion billions. Roughly 93% of the mass of the human body is made up of just 3 elements: oxygen, carbon, and hydrogen. Oxygen and hydrogen are predominantly found in water, which makes up about 60% of the body by weight. Carbon is maybe the most important element for life. It can easily bond with other atoms, which allows for the building of long, complex chains of molecules which make up the solid part of you. The remaining 7% is a tour of the periodic table of elements. Nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iron, fluorine, zinc, copper, iodine, selenium, chromium, manganese, molybdenum, cobalt, lithium, strontium, aluminium, silicon, lead, vanadium, arsenic, and bromine. Whew. By the way, this also means you're about 0.5% metal, no matter what your favorite music is. Anyway, these elements perform various functions like enabling oxygen transport, building of bones and cell structures, carrying signals, driving chemical reactions, and a lot more. Your body is in a constant state of transition. Every 16 days, 75% of you has been replaced because a healthy human exchanges about 100% of their water in that time period. Each year, about 98% of your atoms are replaced by new ones, and every 5 years, close to all of the atoms that make up your body weren't there 5 years ago. So, you could call yourself a temporary collection of atoms. But where did these atoms come from? In the beginning of the universe, there were mostly hydrogen and helium atoms. Enormous gas clouds formed over millennia and grew denser and denser until they collapsed under their own gravity, giving birth to the first stars. In the cores of these stars, hydrogen was converted into helium under extreme conditions. After millions of years, the hydrogen became exhausted and the stars began dying. Under super extreme conditions, all elements we know today were created a fraction of a second before they died and exploded in supernovas. They shot most of their contents into space, while the cores collapsed and became black holes. All these elements traveled through space for who knows how long, until they arrived at a different cloud that was slowly forming a new star, our Sun. These elements that once were the insides of a star formed planets and found their way onto Earth, where they enabled life to begin. So we are directly connected to the first stars ever born in the universe. We are part of the universe. The idea of being a deeply connected, minuscule part of an enormous structure is really mind-blowing. We don't know what all this means, or if it means anything at all. We know that we're made of little parts that connect us to everything in the universe, to the beginning of everything. And this is kind of a nice thought. You are not alone. You never were. You never will be. The Solar System. Our home in space. We live in a peaceful part of the Milky Way. Our home is the Solar System, a 4.5 billion-year-old formation that races around the galactic center at 200,000 kilometers per hour and circles it once every 250 million years. Our star, the Sun, is at the center of the Solar System. It's orbited by 8 planets, trillions of asteroids and comets, and a few dwarf planets. The 8 planets are divided into 4 planets like ours: Mercury, Venus, Earth, and Mars, and 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. Mercury is the smallest and lightest of all the planets. A Mercury year is shorter than a Mercury day, which leads to enormous fluctuations in temperature. Mercury does not have an atmosphere or a moon. Venus is one of the brightest objects in the solar system and by far the hottest planet, with atmospheric pressure that is 92 times higher than on Earth. An out-of-control greenhouse effect means that Venus never cools below 437 degrees Celsius. Venus also doesn't have a moon. Earth is our home, and the only planet with temperatures that are moderate enough to allow for a surplus of liquid water. Furthermore, it's so far the only place where life is known to exist. The Earth has one moon. Mars is the second smallest planet in the solar system and hardly massive enough to keep a very thin atmosphere. Its Olympus Mons is the largest mountain in the solar system, more than 3 times as high as Mount Everest. Mars has 2 small moons. Jupiter is the largest and most massive planet in the solar system. It consists largely of hydrogen and helium and is the theatre for the largest and most powerful storms we know. Its largest storm, the Great Red Spot, is 3 times as large as Earth. Jupiter has 67 moons. Saturn is the second largest planet and possesses the smallest density of all the planets. If you had a sufficiently large bathtub, Saturn would swim in it. Saturn is also known for its extended, very visible ring system. It has 62 moons. Uranus is the third largest planet and one of the coldest. Of all the gas giants, it's also the smallest. The special thing about Uranus is that its axis of rotation is tilted sideways in contrast to the 7 other planets. It has 27 moons. Neptune is the last planet in the solar system and is similar to Uranus. It's so far removed from the Sun that a Neptune year is 164 Earth years long. The highest wind speed ever measured was in a storm on Neptune at just under 2,100 kilometers per hour. Neptune has 14 moons. If we compare the sizes of the planets, the differences between them become even clearer. Jupiter is the leader in terms of size and weight. Small Mercury, on the other hand, is even smaller than one of Jupiter's moons, Ganymede. Jupiter is so massive that alone it contains roughly 70% of the mass of all the other planets and has a massive impact on its surroundings. That's a blessing for Earth, since Jupiter draws most of the dangerously large asteroids that could wipe out life on Earth. But even Jupiter is a dwarf in comparison to our star, the Sun. Calling it massive does not do justice to the Sun. It makes up 99.86% of the mass in our solar system. For the most part, it consists of hydrogen and helium. Only less than 2% is made up of heavy elements like oxygen or iron. At its core, the Sun fuses 620 million tons of hydrogen each second and generates enough energy to satisfy mankind's needs for years. But not only the 8 planets orbit our Sun, trillions of asteroids and comets also circle it. Most of them are concentrated into 2 belts: the asteroid belt between Mars and Jupiter, and the Kuiper belt at the edge of the solar system. These belts are home to countless objects, some as large as a dust particle, others the size of dwarf planets. The most well-known object in the asteroid belt is Ceres. The most well-known objects in the Kuiper belt are Pluto, Makemake, and Haumea. Usually, we describe the asteroid belt as a dense collection of bodies that constantly collide. But in fact, the asteroids are distributed across an area that is so indescribably large that it's even difficult to see 2 asteroids at once. Despite the billions of objects in them, the asteroid belts are fairly empty places. And nonetheless, there are collisions over and over again. The mass of both belts is also unimpressive. The asteroid belt has a little less than 4% of our Moon's mass, and the Kuiper belt is only between 1/25th and 1/10th of Earth's mass. One day the solar system will cease to exist. the Sun will die and Mercury, Venus and maybe Earth too will be destroyed. In 500 million years, it will become hotter and hotter until at some point it will melt Earth's crust. Then the Sun will grow and either swallow Earth or at least turn it into a sea of lava. When it has burnt up all its fuel and lost most of its mass, it will shrink to a white dwarf and burn gently for a few billion more years before it goes out entirely. Then, at the latest, life in the solar system will no longer be possible. The Milky Way will not even notice it. A small part of it, in one of its arms, will become just a tiny bit darker, and mankind will cease to exist, or leave the solar system in search of a new home. The Sun. Smooth and round and peaceful. Except when it suddenly vomits radiation and plasma in random directions. These solar flares and coronal mass ejections, or CMEs, can hit Earth and have serious consequences for humanity. How exactly do they work? How bad could they be? And can we prepare for them? While the Sun seems pretty solid, it's actually like a very hot ocean. So hot that it rips atoms into electrons and nuclei, all flowing around each other in a plasma. This plasma is pushed around and shaped by the Sun's magnetic field, similar to how the Sun's gravitational field reaches out to the planets and shapes their orbits. But magnetism is very different from gravity. Magnetism is one part of a dual force, electromagnetism. Electricity creates magnetic fields, and magnetic fields create electricity. On the Sun, the plasma made of electrically charged protons and electrons creates a magnetic field as they move, and this magnetic field then shapes the flow of particles. They're stuck in a dynamic feedback loop called a dynamo, which keeps the Sun's magnetic field alive. This magnetic field stores enormous amounts of energy and leaks out over the solar system. It carries with it a constant trickle of solar plasma like a light rain known as the solar wind, creating a sort of space weather. But it isn't always calm and smooth. As the Sun's plasma churns and flows around itself, its magnetic field gets all kinked and twisted. This creates magnetic knots that build up enormous amounts of energy. When the magnetic knots break, like a tangle of springs exploding outwards, the Sun can vomit plasma and other awful things into the solar system. These solar storms come in many types, like solar flares, a tidal wave of high-energy radiation. They race through the solar system at the speed of light, sweeping up protons in the solar wind, accelerating them into a high-speed solar proton storm. Then there are coronal mass ejections, which rip millions or billions of tons of plasma from the Sun's atmosphere, catapulting it through the solar system at speeds of up to 9 million kilometers per hour. When these monsters hit us, nothing happens on Earth. While even smaller storms can damage satellites, affect radio communication, or be dangerous to astronauts, for people on the surface, space weather is harmless. Earth's atmosphere protects us from the worst effects of a solar flare by absorbing the blast of X-rays high up in the atmosphere, well before it reaches the surface. The electrified plasma from a CME is deflected by the Earth's magnetic field, diverting the energy storm to the north and south poles, where energetic particles fall into the atmosphere, causing the atmosphere to glow and creating beautiful auroras. As with any sort of weather, most of the time things are fine. Sometimes there are hurricanes though, or in the case of the Sun, solar superstorms. And we know that they happen once or twice every century. If one were to happen today, we would first detect strong solar flares, a sort of flash before the much more dangerous thunder. The thunder is a CME, consisting of billions of tons of hot magnetic plasma that crosses the 150 million kilometers between the Sun and Earth in less than a day. When it arrives, it causes a shock wave that violently compresses the Earth's magnetic field and transfers energy into the magnetosphere. But it can get worse. If the magnetic field of the CME is aligned to Earth's in just the right way, the two magnetic fields merge. As the magnetic cloud passes over Earth, it stretches the Earth's field into a long tail. Eventually, the energy stored in the tail becomes too much to contain. It snaps and explosively releases its energy towards Earth. A geomagnetic storm has begun. A few hundred years ago, nobody would have cared. This storm gushing over the Earth is not relevant for machines made out of meat and bones. But it's very relevant for machines made out of metal and wire. Remember the dynamo? Magnetism creates electric currents. Earth in the 21st century is covered in millions of kilometers of wires transporting electricity and a complex grid of machines like transformers that make this transfer possible. A CME's energy can induce currents in our power grid that can either completely shut it down or, worse, destroy the transformer stations that keep our grid running. This has happened already, like when the Quebec power grid failed after a strong solar storm in 1989. But in general, our engineers know how to deal with these storms, and so we usually don't even notice. The last time a solar hurricane washed over Earth was in 1859, the Carrington event, the largest geomagnetic storms ever observed on Earth. Massive auroras occurred as far south as the Caribbean. In some places, they were so bright that people got up thinking the sun was rising. Luckily, we only had one sort of modern technology: telegraph systems. They failed all over the world, shocking their operators and chucking out sparks. Today, we have a tad more technology, and our luck may run out soon. Another bad solar storm is bound to happen eventually. A storm as strong as the Carrington event missed Earth only by a small margin in 2012. Studies projected that it would have inflicted serious damage to electronic systems globally, costing up to $2.6 trillion to the US alone. The time to replace all the damaged systems was estimated at between 4 and 10 years. It's hard to say how bad it could have been. Experts disagreed. Some assumed there would just be temporary blackouts, but others worried it could be much worse. We won't know for sure until a big solar hurricane hits us. The probability of such an event is estimated to be 12% per decade. That's about a 50-50 chance of at least one in the next 50 years. And there is more unsettling news. A 2019 paper found that even calm stars like our Sun can create superflares every few thousand years. Eruptions orders of magnitude stronger than the strongest storms we have observed in the solar system. If such a storm hits us unprepared, the consequences could be catastrophic. It's hard to overstate how much we depend on electricity. It's not just the lights at home, it means no computers, no communication, no navigation. A sustained power outage might lead to a breakdown of the supply chain, water supply systems failing, and hospital generators running dry. Supermarkets not being refilled while food rots in the fields. The lack of power might make it extremely hard to reboot our broken power grid, taking years or decades to restart our starving civilization. Okay, time to panic? As much as daily newspapers might like for solar storms to send us back to the Stone Age, they probably won't. Fortunately, even though solar storms aren't preventable, virtually all of their nasty side effects are. Scientists observing the sun have a few hours up to a few days to see a CME coming. And the engineers working the systems that keep the world running are well aware of the risks posed by solar storms. Transformers and substations can be taken offline. Short preventative blackouts, or in other words, by unplugging stuff. Engineers can open up extra lines to dissipate the extra power, and with investment and upgrades cheap compared to those other natural disasters require, we could protect the world's electric grid against even the nastiest of storms. But we do need to prepare. While the risk is manageable, it is real. For while our sun bathes us in warm and pleasant light, one day it might send a monster our way that we better be ready for. The largest things in the universe are black holes. In contrast to things like planets or stars, they have no physical size limit and can literally grow endlessly. Although in reality, specific things need to happen to create different kinds of black holes, from really tiny ones to the largest single things in the universe. So how do black holes grow? And how large is the largest of them all? This video will not discuss how black holes work or how they form, since we've looked at that in detail in our black hole and neutron star series. You can check them out afterwards. For now, we're interested in finding the largest thing in the universe. Let's start really small. Primordial black holes. The smallest kind of black holes may or may not exist. If they do, they're probably the oldest objects in the universe, older even than atoms. They would have formed just after the Big Bang, when the universe was so dense with violent energy that any tiny pocket that was just slightly more dense than its neighbors could produce a black hole. The smallest primordial black hole that could still be around would be 8 trillion kilograms or so, the mass of a big mountain. And yet they would be no bigger than a proton. A primordial black hole with the mass of Earth would barely be larger than a coin. This makes them very hard to find, so we haven't actually observed any yet. If they exist, they may even be the mysterious dark matter that holds galaxies together. Let's move on to the kinds of black holes that we know for sure are out there. Stellar black holes. To make a black hole, we need to compress enough matter so that it collapses into itself. After that, the more mass we throw at it, the larger it becomes. In today's universe, only the most violent cosmic events can create the necessary conditions, such as the merger of neutron stars or when the core of a very massive star collapses in a supernova. To have a unit to work with here, we'll use the mass of our Sun, about 2 million trillion kilograms. The smallest known black hole has 2.7 times the mass of the Sun, which works out as a sphere around 16 kilometers in diameter, large enough to cover Paris. Another lightweight black hole is the companion to the V723 Mon red giant star. This star is 24 times larger than our Sun, 30 million kilometers in diameter. And yet, it's thrown around by a tiny black hole just 17.2 kilometers wide. This tiny thing bullying the star is so much smaller that we can barely even show them in comparison. One of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit. As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our Sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica. To grow much larger, black holes have to either devour a lot of stars or, better, merge with one another. The instruments that make it possible to detect these mergers are very new, so we're currently discovering a lot of exciting things. Like 2 massive black holes that we detected in a galaxy 17 billion light-years away. As they spun around each other violently, they released more energy in the form of gravitational waves than the combined light from all the stars in the Milky Way in 4,400 years. The new black hole they formed is about the size of Germany and is 142 solar masses. And here we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time. Until we suddenly hit black holes that are millions of times more massive. Which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to explain their existence today. The universe is simply not old enough for these supermassive black holes to have formed by eating stars and merging with each other. Something else must have happened. To explain how we got the largest black holes in the universe, we might need the largest stars that ever existed. Quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our Sun is like a grain of sand next to them. We don't know if quasi-stars actually existed, but they're an interesting concept when it comes to supercharging black hole development. The idea is that the matter in the early universe was so dense that quasi-stars could grow to thousands of times the mass of our Sun. The cores of these stars might have been crushed by their own weight so much to actually collapse into black holes while the star was still forming. In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. And so these quickly growing black holes might have been able to consume the quasi-star for millions of years and grow far bigger than any modern stellar black hole. Black holes several thousand times the mass of the Sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes. So now we arrive at the kings of our universe, the largest single bodies in existence. The centers of most galaxies contain a supermassive black hole, and they are monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar masses that is calm and collected and just does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass, its radius is still only 17 times our Sun. Smaller than most giant stars, but millions of times more massive. Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the Sun in the solar system. An anchor that glues everything else together and forces it into an orbit. But this is a misconception. While the Sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their galaxy. The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the gravitational effect of dark matter which holds them together. Many supermassive black holes aren't gentle giants, especially when they're feeding on the clouds of mass in their galaxy. The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 115 times larger than our Sun in the sky, and we'd be burnt to a crisp in seconds by its glowing hot accretion disk. At this point, black holes become so large that stars seem ridiculously tiny compared to them. The galaxy Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our Sun, it would swallow all the planets and stretch halfway to the edge of our solar system. It's devouring so much mass and material that it churns its disk into a kind of magnetic funnel, spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light-years in diameter. That's 2.5 Milky Ways wide. Another pretty large supermassive black hole sits in the galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo of, or rather, of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large that it covers our entire solar system. And yet, there is a scale even above these kinds of objects. Ultramassive black holes. Now we reach the most massive black holes, perhaps the largest single bodies that will ever exist. These black holes have eaten so much that they've grown to tens of billions of solar masses, their gravity the engine for a quasar, an accretion disk shining brighter than thousands of galaxies full of stars. So massive that they deserve a title of their own: ultramassive black holes. The ultramassive black hole at the center of galaxy OJ287 is 18 billion solar masses. It's so big that it has a supermassive black hole nearly 40 times larger than Sagittarius A star orbiting it. This thing defies imagination and is really hard to compare to anything. It can comfortably fit 3 solar systems side by side inside of it. Let's end this insane competition and get to the King of Kings. TUN 618, a black hole that we can observe consuming galaxies worth of matter, is shining with the brightness of 100 trillion stars, visible from 18 billion light-years away. It has an incredible 66 billion solar masses. A black hole so large that it would take light a week to reach the singularity after crossing the event horizon. About 11 solar systems could sit inside of it, side by side. It may very well be the largest single body in the universe, but in reality, it's probably even larger. Since Ton 618 is so far away, we only see what it looked like 10 billion years ago. In any case, black holes are scary and mysterious and gigantic. They'll be here after everything else dies and growing larger and larger. Okay, now let's do the trip again. From the smallest possible black hole all the way up to the largest. Let's try something new today. We can call it Behind the Lies, a short behind-the-scenes bit about the necessary inaccuracies in this video, because it's not really actually possible to rank black holes like trading cards. How so? Well, while we've catalogued millions of stars, we really only have good data on a couple of dozen black holes. That's because black hole gazing wasn't really a thing until 50 years ago, and technically still isn't because we can't see black holes. We can only derive their properties from studying their gravitational effects on the matter around them, like the orbit of stars that come close to them. This effect depends on the mass of the black hole, which we can approximate at the most basic level with Kepler's laws. But this comes with huge uncertainties and error bars. Then we have to convert mass to size next, which brings new uncertainties. For example, we calculated the radius from the mass using the Schwarzschild equation, which for the sake of simplicity assumes black holes are perfectly round and don't spin, a kind of black hole that doesn't really exist. The reality is that physics on these scales is a bit fuzzy. So some of the black holes we talked about here may be way smaller or way bigger. We just don't know for sure. We shimmied around this problem by comparing different sources with different kinds of values and using different mass calculations to arrive at a standardized list that allowed us to be as accurate as humanly possible. You can look at all of this in our source doc. As a result, this script was written with the tears of experts we drove crazy with our obsession for the best values they could live with. In this process, tons of stuff got cut and didn't make it into the final video. But luckily we found a way to not waste all of it. We've created a lot of black hole merch, spanning the whole range from somewhat bonkers to more serious. This way, we get to explore a topic from different angles, and you get to continue having fun with black holes after this video ends. Black holes can destroy everything, but can they be destroyed? What happens if we push physics to the absolute limits, maybe even breaking it and the universe in the process? Let's create a tiny black hole about the mass of our moon in the Kurzgesagt labs and try to rip it apart. Experiment 1. Nuke it. Big booms break things, so to set the mood, let's explode the world's entire nuclear arsenal around our black hole. Boom. Black holes swallow whatever crosses their event horizon, matter and energy. And since E equals mc squared, all the energy that enters a black hole increases its mass. The mass of a black hole is proportional to its size, so as we nuke our tiny black hole, it just gets bigger and more massive. Experiment 2. Antimatter. Matter and antimatter annihilate each other. What will happen if we throw a moon's massive antimatter at it? Unfortunately, when an object enters a black hole, the black hole will completely delete its past identity, whether it's made of matter or of antimatter. Black holes only care about gravity, which only depends on the total mass energy of an object. And the mass of a particle is the same as its corresponding antiparticle, so throwing an anti-moon has the same effect as throwing a moon. The black hole just gets more massive. This deleting ability of black holes is pretty interesting. It means that despite their size and power, black holes are, in a way, similar to elementary particles. An elementary particle like an electron is an extremely simple object, fully specified by just 3 numbers, its mass, spin, and charge. And amazingly, the same is true for black holes. They have a mass, they can rotate, and carry an electric charge. Once a black hole forms, it doesn't matter if it comes from a collapsed star, an anti-star, or a banana, it will always be fully described by those 3 numbers, nothing else. But if a black hole is basically a weird particle, could we destroy it with an anti-black hole? Experiment 3. Anti-black hole. How exciting! A particle has the same mass as its corresponding antiparticle, but opposite charge. Since a black hole has mass and electric charge, its corresponding anti-black hole should have the same mass and opposite electric charge. What if we make them collide? Sadly, the charge will just add up and cancel out. So after the collision, we'll just get a new black hole twice as massive with no charge. Okay, we need to think bigger and stretch physics harder. Experiment 4. Destroy the event horizon. It's true that a black hole can carry spin and charge, but even for these crazy objects, there are limits. If the spin or the charge of a black hole becomes too large, something really weird will happen. The event horizon will dissolve. In a simplified way, we think of black holes as hiding a singularity inside, an infinitely compressed mass with such strong gravity that absolutely nothing can escape from its surroundings, not even light. This is why a black hole looks like a black sphere of nothingness. The event horizon is the outer edge of this ultimate prison. Cross it and you'll never be able to come back. But when a black hole rotates, it works a bit like a spinning washing machine. It's as if the rotation wants to repel nearby objects and push them out of the black hole, which doesn't happen because its gravity is so strong. But if the rotation gets too fast, this effect will win and the event horizon will disappear. Nearby objects won't be imprisoned forever anymore. The same thing happens with the electric charge. Make it too large and our ironclad jail will break open. If we manage to destroy the event horizon, the singularity would still be there, and objects would still naturally fall towards it. If you hit it, you would still die horribly and quickly. But the vicinity of the singularity won't be an inescapable prison anymore. You could get as close as you want and come back. This should count as destroying the black hole. Can we do it? Experiment 5. Overfeeding. All we have to do is to overcharge or overspin the black hole. We could do this by throwing objects with a small mass and a lot of charge or angular momentum so that the charge or spin increases faster than the mass. We have to overfeed the black hole until it reaches the point where it breaks open. However, whether you can actually do this is the subject of passionate argument among physicists. Think of a charged black hole. Equal charges repel each other, and the more of the same charges you squish together, the more they push back. So let's say that we have a negatively charged black hole and we want to overfeed it with electrons, for example, whose charge is far larger than its mass. The electrons will feel an electrostatic repulsion, and the more electrons we throw, the larger the negative charge of the black hole will be and the stronger the repulsion. But once we reach the upper limit, the electrostatic repulsion will be so strong that it won't allow any more electrons to come in. At this point, the black hole will refuse to be overfed. With the spin, it's similar. Once the black hole reaches its upper limit, it won't gobble more spin. But some scientists have discovered what looks like a loophole. If an instant before the black hole reaches the limit, we throw the right amount of matter in just the right way, it looks like we could actually overfeed it. Most scientists are skeptical, but let's give it a try anyway. The end? Breaking physics. There is a catch though. The event horizon of a black hole hides the singularity. So destroying the horizon would leave us with a naked singularity, one that is not hidden by an event horizon. And this poses a problem. It could mean the end of physics as we know it. There's a big dirty secret about black holes. Contrary to widespread belief, the singularity of a black hole is not really at its center. No, it's in the future of whatever crosses the horizon. Black holes warp the universe so drastically that at the event horizon, space and time switch their roles. Once you cross it, falling towards the center means going towards the future. That's why you can't escape. Stopping your fall and turning back would be just as impossible as stopping time and traveling to the past. So the singularity is actually in your future, not in front of you. And just like you can't see your own future, you won't see the singularity until you hit it. But you also can't hit something that's in your future, only sort of experience it, like you'll experience your next birthday when it happens. Singularities that are in the future are not a problem because we can't see them or interact with them. But a naked singularity would be in front of us for all of us to see. What would we see? Well, the whole point is that it's impossible to know. A singularity is a region of infinite gravity, and gravity is the bending of space-time. At a singularity, the bending is so radical that the fabric of space-time is literally broken. Space and time don't exist anymore. This means that you can't predict anything, since predicting means making a forecast about where and when something will happen. But where and when have lost their meaning. So we have an unpredictable thing with infinite gravity and therefore infinite energy. This means that anything could come out of it for no reason, from a pile of bananas to lost socks or a solar system. Predictability, causality, and physics as we know it would break down. We think that singularities should exist in nature because we can prove that under very general conditions, gravitational collapse leads to the formation of singularities. However, scientists think that nature forbids the formation of naked singularities. Something enforces the creation of an event horizon around them to prevent their insanity from infecting the rest of the universe. Without event horizons, physics may not make sense at all. So although black holes have been portrayed as the ultimate monsters of the universe, they may actually be the heroes that keep us safe from the madness of singularities. So if we do destroy the horizon, we might destroy the fundamental rules of the universe. You know what? Let's not do that. Conclusion: the safe option. As far as we know, there's just one safe method to destroy a black hole: wait. All black holes emit tiny particles, a phenomenon called Hawking radiation. This process causes them to slowly lose mass until they eventually evaporate, leaving behind no horizon and no naked singularity. The time it takes for a black hole to completely evaporate depends on its mass. For our mini black hole the size of a speck of dust, it will be about 10 to the power of 44 years, 10 billion trillion times the present age of the universe. So is it possible to destroy a black hole? Yes, we just have to wait. The universe is going to die one day. But how? Well, it turns out our cosmic fate will be decided by a fight between two titans. The two warriors deciding the fate of the universe. Our universe was born 14 billion years ago in the Big Bang and has been expanding ever since. For some reason, new empty space is being created out of nothing between galaxies. Space itself is becoming bigger. Will it go on forever, or will it stop one day? Today, we think the universe is at the mercy of two cosmic demigods fighting for dominance. The first one is all the stuff in the universe: galaxies, gas, dark matter. While they're very different, they just want to do one thing: get together. Matter is attracted by matter, pulled together by gravity. And gravity also pulls on the universe as a whole, slowing the expansion that started at the Big Bang. Our second warrior is empty space. While it seems, well, empty and powerless, empty space has an intrinsic energy. We don't really have an idea what this energy is or why it's there. It's really a placeholder that fills a blank in our understanding of reality. But it's got a cool name: dark energy. Dark energy pushes things apart, a sort of anti-gravity that accelerates the cosmic expansion. So, we have all the matter in the universe pulling in, and empty space infused with dark energy pushing out. Whoever wins will kill the universe in fun ways. But who will win? It all depends on the mysterious dark energy. Will its strength stay the same? A common assumption just because it keeps our models simple? Or will it get weaker? Or will it get more powerful over time? 1. Constant dark energy. Heat death. If the strength of dark energy stays constant, it will win the war. Since space is growing, matter is getting more and more diluted, like sugar in a cup being filled with more and more tea. But as the universe expands, new empty space is created, which brings more dark energy, which pushes everything apart even more, which creates more empty space, which makes the universe grow even faster. A feedback loop that will make the universe expand at an exponential rate. Every 12 billion years or so, it will double in diameter, forever. But while dark energy is winning the war, matter is winning at least one battle. At short distances, it can keep things together. Local galaxy bubbles can overcome the push of dark energy. In a few billion years, our local group of galaxies will merge into a gigantic ball with trillions of stars. It will soon become our last view of the cosmos. All other galaxies will be pushed away by the expansion. For us, it will look like the rest of the universe is rushing away, until in a few 100 billion years, we won't see other galaxies at all. We'll be alone, surrounded by a seemingly infinite dark void. In about 100 trillion years, all the stars of our supergalaxy will have died out. All gas that could create new stars has been consumed, and no new gas can come in. The galaxy will be dark and filled with stellar corpses. Over quadrillions of years, white dwarfs and neutron stars will slowly cool until becoming truly dark, turning off the last lights of the universe. All structures, big and small, will slowly dissolve. One by one, all dead stars and planets will leave the supergalaxy, which slowly dissolves over sextillions of years. Every object will end up on its own, which means that dark energy takes over again, creating more and more empty space between everything. Objects will be so far apart that it will be as if each had a universe for itself. Not much happens anymore until in a googol years, all black holes will have evaporated. In the end, entropy and dark energy won't stop until their job is finished. Over time spans you might as well call forever, all remaining structures might even dissolve into single particles that will be pushed away from each other by an ever-growing empty space. Imagine a whole universe with just a single lonely particle traveling through nothingness. This is the final state, the true end, the big freeze, or heat death, a completely featureless, cold, and eternally expanding universe. Nothing will ever be able to happen again. Forever. Phew, well, that was a bummer. What else could happen? 2. Increasing dark energy. Big rip. What if dark energy gets stronger? In this case, empty space won't just win over matter, it will literally rip it to pieces. In the Big Freeze scenario, matter lost the war but won some battles. But here, matter wins nothing. Dark energy is growing stronger over time, overcoming the pull of gravity and creating new empty space at smaller and smaller distances. In this scenario, things will escalate quickly. It could start as early as 20 billion years from now. First, dark energy will create empty space between individual galaxies. Our galaxy will leave its local cluster and begin to drift alone in a rapidly inflating and ever darker cosmos. Some billion years later, empty space starts to push between individual stars, dissolving the galaxy. If you live on a planet in a star system, the night sky will start looking sad and gloomy, as other stars are pushed too far away to be seen. A few million years after the sky turns dark, dark energy starts to create empty space inside star systems. Your planet is pushed away from its star, and all life in the universe freezes to death. There's not much time left, as a few months later, dark energy is creating empty space inside solid objects. Stars, neutron stars, planets, asteroids, everything solid is being ripped into pieces. If you're on a spaceship, you only have a short time before you are ripped apart. Half an hour later, even atoms are destroyed as new space is being created so furiously that electrons and nuclei are separated. Now the universe has just a fraction of a second left. In this final moment, only dying black holes remain, drained and defeated by dark energy. They're tiny, septillions of times smaller than an atom, and they explode with the power of a trillion supernovae in a trillionth of an octillionth of a second. Finally, the very fabric of reality is torn to its core, obliterating space-time itself. The Big Rip. Space and time have lost their meanings, making it impossible to predict what will happen next. 3. Decreasing dark energy. Big crunch. Poor matter. But there is one scenario where it wins. If the strength of dark energy decreases with time, and if this reduction is strong enough, the pull of gravity will win and all the things in existence will move towards each other, unfortunately making the universe collapse into itself. No one knows when this might begin, but it could be as soon as a few 100 million years. What will it look like? As the universe begins to contract, over billions of years, galaxies and galaxy clusters approach each other until they eventually collide. They're mostly made of empty space, so a collision is like the gentle merger of two clouds. At any rate, first galaxies and later individual stars get closer and closer. As the universe goes on collapsing, you might worry about stars and planets eventually crashing against each other. This will happen, but it's not your worst problem. If space itself shrinks, this also concentrates all the radiation emitted in the past by all the stars, supernovae and quasars that ever existed. Now, empty space is filled with radiation. The dark nothing between stars is heating up, making life unpleasant and then impossible as planets just burn. Slowly at first, then rapidly, space gets as hot as it was after the Big Bang. Stars are pretty hot, but now the space around them is hotter. They're literally boiled from the outside. As the universe collapses into itself, all galaxies and all stars merge into a single ball of hot plasma. The Big Crunch is complete. From here on, there are two possibilities. Either the universe will collapse completely into a singularity, a point of zero size and infinite density without space and time, the way it might have been before the Big Bang. Or the universe could bounce back, restarting the cosmic expansion, creating a new baby universe. Somewhat poetic, really. Everything died, but everything is reborn. But to be clear, we have zero evidence that this has happened before or will in the future. So what will happen? Most scientists think that dark energy will stay constant, so the likely fate of the universe is heat death, eternal cold, and utter boredom. Which seems sad, but has a huge upside. In this scenario, we get to have the universe for the longest. It gives us trillions of years to expand, jump from star to star, maybe even from galaxy to galaxy. We might even find a way to keep consciousness around forever. We don't know. So we just have to wait and see, and make the most of the amazing universe we have right now. You might be inside a black hole that's inside a black hole that's inside a black hole. Everything in existence could be black holes all the way down. It turns out black holes are much weirder than you think, and they break the universe much more than is usually explained, destroying time and space. And they may actually create infinite universes in the process. But before we can get to that, let's first build a black hole out of air. Everything can become a black hole if you squeeze it to a critical limit. You'd need to squeeze Earth down to the size of a coin for it to turn into a black hole. The Sun needs to be squeezed down to the size of a small city to become a black hole. And if a lot of mass is concentrated in a really tiny space, you get something super dense. This is usually how black holes are explained. Stuff becomes super dense and collapses into a black hole. But actually, you don't need any ultra-dense stuff to make them. We're ignoring some maths here, but all you really need to know is one thing. The larger black holes get, the less dense they are. So, really large black holes are kind of thin. A sun-mass black hole is only about 6 kilometers wide and has a density of about 1 Himalayan range per cubic meter. The supermassive black hole at the center of the Milky Way has a mass of 4 million suns, a diameter of 24 billion kilometers, and a density of 6 blue whales per cubic meter. The ultramassive black hole IRAS 2100-4156 has a mass of 3.8 billion suns and is as wide as the solar system. But because it's so large, it is only as dense as air. This means, at least in theory, that if you take a gigantic balloon and fill it with undecillions of tons of air, the moment it gets to the size of a solar system, an event horizon suddenly forms and it turns into a supermassive black hole, without violence or squeezing. So now, let's think big. What do we need to make a black hole the size of the universe? A universe-sized black hole. The chunk of the universe that we can see from Earth is a sphere with a radius of 45 billion light-years, filled with hundreds of billions of galaxies, lots of gas, and a bunch of other things. If you add them up, it has the mass of about 1 million billion suns. Which sounds a lot, but on average, the universe is not very dense. If we break up all the galaxies, stars, gas, and energy and spread them equally inside the volume of the universe, we get an average density of about 5 hydrogen atoms per cubic meter. You can imagine this as the sort of ultra-thin cosmic air that makes up the universe. What would happen if we take a balloon as big as the observable universe and fill it with cosmic air? Well, it turns out that all the mass in the observable universe is more than enough to create a black hole. Actually, it's enough to make a black hole 10 times larger than the observable universe. But that can only mean one thing. We should be living deep inside a truly gargantuan, cosmic-sized black hole. There's one catch though. We know that our universe is expanding, and an expanding universe is not what you'd expect to see if you were inside a black hole. So our universe can't be a black hole, at least not in the naive way we've just described. Except there's a wild and mind-bending trick the universe could play on us. To find out how, let's jump into a black hole and die. A whole universe born inside a black hole. We usually imagine black holes as spheres with a singularity at their center, a point where all their mass is concentrated so much that our maths breaks down. But this is a lie. They are so much weirder. From the outside, a black hole looks like a normal black sphere, but the inside is where things stop making sense. Black holes warp the universe so much that at the event horizon, space and time switch their roles. Inside a normal sphere, space is finite, but time goes on forever. But inside a black hole, it's the other way around. Space goes on forever, but time is finite. So once inside, you see an infinite universe with no center. The geometry is too complicated, so we're simplifying. But basically, you could walk forever in one direction, or walk in another direction and arrive at the same place again. But not only that, inside a black hole time is finite and it's now running out. So after a while you start to notice that space itself is slowly changing. In one direction space is being stretched, while in all other directions space is shrinking. The whole universe is being squeezed, kind of turning into a collapsing spaghetti. Sooner or later the whole black hole universe collapses into itself. All of space, every single part of it, is turning into a singularity. So the singularity of a black hole is not at its center or in any direction at all. It's in the future of whatever falls inside. We made a whole video about this if you want to learn more. So the singularity is not a place where you can go, it's an event in time that happens. Once it happens, you and everything else that fell inside the black hole will be mercilessly crushed into an infinitely small region with infinite gravity and infinite energy. Time, space, none of it matters anymore. Both kind of stop existing in ways that we would recognize. And then, is this the end? Well, maybe not. This collapse of the black hole universe into a singularity looks like one of the scenarios for the end of our universe, the Big Crunch, where long after the Big Bang the whole universe collapses into a singularity again. But if there's a big crunch, there might be a big bounce, like a rubber ball that you've squeezed too much and that suddenly rebounds. Space might expand again. So a new universe could be born inside a black hole. The funny thing about this scenario is that nothing has changed in the slightest outside the black hole. Watching from the outside, it's still a black sphere of nothingness, and yet on the inside, a new universe has been born. So maybe our universe was born like this, and we are all actually inside a black hole. But if our universe can also create black holes, they might give birth to new universes. Is our black hole universe also just part of a universe further up that's also a black hole inside another universe? Is there an end to it? Is there one original universe? Is the cosmos black holes inside black holes inside black holes? Infinite black hole universes. If the universe creates black holes that create universes, that then create new black holes that create new universes, this cosmic self-reproduction would be subject to natural selection. A Big Bang is a chaotic and messy event, so it's possible that the new daughter universes would not always be fully identical to their mums. Sometimes physics may be slightly different, with some fundamental values higher or lower, and so some universes might be able to create loads of stars, planets, and black holes. Others might not, maybe creating a uniform cosmic soup where no stars, planets, and black holes form. But if all universes are born inside black holes, in the long run all universe lines that don't create loads of black holes would die out. The universes with the conditions for loads of black holes would become the most common and spawn the most daughter universes. Survival of the fittest, but with universes instead of organisms. Our observable universe alone has created at least 10 to the power of 17 black holes so far. So maybe our universe has the physics and laws it has because it was born after a long process of cosmological selection that favored the production of tons of black holes. And that would have a lovely side effect. If universes are optimized to create as many new black hole universes as possible, they're optimized to create loads of galaxies and stars. And thereby also, by accident, the conditions for life to emerge. So universes that are the best at creating new universes are also the best at creating life. If this scenario is true, who knows how many bazillions of black hole universes might be out there, all with stars and planets potentially home to others like us. So, is our universe like this? The truth is we don't know. While these ideas are based on real science and work on paper, they're speculative and not testable. Also, cyclic universes don't actually explain why the universe exists in the first place or why it is the way it is. Instead of providing answers, these are really just new questions in disguise, so keep that in mind before getting too excited. But isn't it just wonderful and heartwarming that we're living in a universe where ideas as big as this one are even thinkable? There might be so much life. And if new universes are created constantly, maybe life will go on forever. The 14 moons of Neptune are a strange bunch. Most of them are small potato-shaped pieces of ice and rock. Some are so far away from Neptune that they need 29 years to circle Neptune once. Almost all of them are asteroids trapped by Neptune's gravity. 99.5% of all the mass around Neptune is concentrated in Triton. It's the 7th biggest moon and more massive than all other known moons in the solar system that are smaller than itself combined. Its surface area is about as big as the mainland of Russia and Australia together. Also, Triton is one of only 4 objects in the solar system that we know is geologically active. Triton orbits Neptune in the wrong direction, against the rotation of Neptune, which is unique in our solar system for an object as big as Triton. We can conclude from this that Triton hasn't always been a moon of Neptune, but probably was a dwarf planet that was forced into submission by Neptune when the solar system was younger and more chaotic. The most popular theory here is that Triton was once part of a double system. When Neptune migrated to the outer edges of the solar system, its gravity interfered with the double system and catapulted the other object into space, while Triton was forced into orbit. This would have disrupted the orbits of other Neptune moons rather violently and would most likely have either pushed them away from Neptune or let them collide or crash into Neptune. This would explain why Neptune's moons are so dominated by Triton. But this will end one day. Triton is being slowed down by Neptune, and eventually it will either crash into it or be ground by Neptune's gravity into a huge ring system similar to Saturn's. So don't buy real estate on Triton. Human history is told by the energy we use. At first we had to use our muscles, then we learned to control fire. We industrialized the world using coal and oil and entered the atomic age when we learned how to split a nucleus. At each step we increased our energy harvest to a scale never seen before and advanced as a species. Currently, we're slowly transitioning to renewables, and if we're lucky, fusion energy will become viable in the future. As humanity progresses further, if we don't destroy ourselves or our habitat, we will likely gain complete control of our planet's resources. At that stage, we'll probably begin to look outwards for new places to expand into. But space is hard, and establishing a serious human presence in the solar system will require ungodly amounts of energy. Luckily, we know where to find it. The Sun, the ultimate source of energy. A furnace 100 quintillion times more powerful than our most efficient nuclear reactor. It shines with the energy of 1 trillion nuclear bombs per second. So how do we get this energy? Not some of it, all of it. If we want to collect the most energy physically possible, we'll have to build the largest, most ambitious structure in the universe, the Dyson sphere, a megastructure that encompasses a whole star to capture its power output. For an intelligent species, building a Dyson sphere is a technological leap on a par with the discovery of fire for our ancestors. the transition from a planetary species to an interstellar species. It would usher in an age of exploration and expansion on a scale we can barely imagine. So, what would it look like? A solid shell enveloping the Sun is probably not the way to go. A large rigid body like that would be vulnerable to impacts, possibly shattering. It would be liable to drift and could crash straight into the Sun. A more viable design for a Dyson sphere might be a Dyson swarm, an enormous set of orbiting panels that collect the Sun's power and beam it elsewhere. Such a swarm would give humanity basically unlimited energy. But building it won't be easy. The Sun is very big, so we need a lot of satellites. If each satellite is a square kilometer, we'd need around 30 quadrillion to surround the Sun. Even if they're built as lightly as possible, we need about 100 quintillion tons of material. And then we need the energy to actually put the parts together and deliver them to their positions around the Sun. On top of all that, we need to have a permanent infrastructure set up in space to start building. Let's assume for the purposes of this video that our descendants will take care of that and want to create the megastructure. We can sort the challenges into three main categories: materials, design, and energy. To get the vast amounts of raw materials required for our Dyson swarm, we'll have to largely disassemble a whole planet. Of the planets available, Mercury is the best candidate. It's the closest to the Sun and very metal-rich. Close to the Sun also means less moving stuff around. And Mercury has no atmosphere and only about a third of the surface gravity of Earth, making it comparatively easy to launch material into space. Next, we should consider the design of our swarm. Simpler is better. Conventional solar panels are far too intricate and short-lived. Our satellites need to operate without repairs or intervention for astronomically long times, and they need to be cheap to produce. They're most likely going to be enormous mirrors, which refocus sunlight to central collecting stations like in concentrated solar power on Earth. To build and launch them efficiently, they must be incredibly light, made of little more than polished metal foil bound to some supports. And last, we need the energy to build and launch the swarm itself. Taking apart a planet and launching things into space requires an enormous amount of energy. For example, if we used all the fossil fuels and uranium on Earth and we were perfectly efficient, we could only launch as much mass as Mount Everest into space. A rather meager accomplishment compared to planetary disassembly. To get the energy needed to build a Dyson sphere, it's almost as if you're going to need the power output of a Dyson sphere. But that's okay. There's plenty of sunlight to be had on Mercury, so let's get to work. Humans are expensive to keep alive and are very sensitive to the environment, so we'd want to automate as much as possible. Ideally, we'd have a small crew of controllers who oversee an army of autonomous machines doing the actual work. There are four major pieces of technology required: solar collectors, miners, refiners, and launch equipment. The solar collectors are going to give us the energy we need to disassemble the planet. To start, maybe we deploy something like 1 square kilometer of them, either as mirrors or as traditional solar panels. They'll provide the energy to run our miners, which strip mine the surface of the planet, and our refiners, which extract valuable elements and fabricate them into our swarm satellites. To get them into space, we need a creative and efficient solution. Rockets are too expensive and difficult to deorbit and reuse. Instead, we'll want to use a sort of railgun, a long electromagnetic track which launches our satellites at high speeds. Our swarm satellites would be packed tight for launch, unfurling like an enormous origami once in orbit. From this point, we can take advantage of exponential growth, using the energy of the existing parts of the swarm to build more infrastructure on Mercury and launch new panels faster and faster. Each panel provides the energy to build another. Those two work together to build the next two. 4 become 8, 8 becomes 16, and so on. Within just about 60 doubling times, the Sun would be completely surrounded by solar panels. And this can happen quickly. If a square kilometer of solar collectors takes a month to build, we could be done in a decade, if only our infrastructure on the planet's surface can keep up with the quickly growing budget of energy. Even collecting 1% of the Sun's energy is an unbelievable change in our species' energy budget. we could create the infrastructure to beam basically unlimited amounts of energy around the solar system for all sorts of projects. Colonies on other worlds, terraforming planets, constructing more megastructures, or even traveling to other stars. It could be the start of an interstellar civilization. Based on physics alone, this is not just possible, but easy. It's such a simple process and such a necessary step for any species to expand beyond their home planet that many astronomers think there are probably Dyson spheres already out there in the Milky Way. We haven't spotted any yet, but they could be there. It's far from certain that humanity will ever get to this point. Our attention is too often focused on short-term political gains and conflicts that will not matter in the long run. But if we survive the challenges we've set ourselves, we could potentially become the first species in the universe to create a structure with the scope of a star. If we do it, the only limitation left will be our own imagination. What is the true nature of the universe? To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away. But the more we learn, the more complicated and weird our stories become. Some of them so much so that it's really hard to know what they're actually about. Like string theory, a famous, controversial and often misunderstood story about the nature of everything. Why did we come up with it, and is it correct, or just an idea we should chuck? To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless, even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore, elementary particles. But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But in quantum physics, shorter wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it gets a kick. By looking at a particle, we change it. In quantum physics, we cannot know where a particle is and where it's going with absolute precision. This fact is so important that it has a name: the Heisenberg uncertainty principle, the basis of all quantum physics. So what does a particle look like then? What is its nature? We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist. But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists could define them and calculate all of their interactions. This can be made precise in quantum field theory, and this solved a lot of problems. All of the standard model of particle physics is built on it, and it predicts lots of things very well. Some quantum properties of the electron, for example, have been tested and are accurate up to 0.000000000002%. So while particles are not really points, by treating them as if they were, we get a pretty good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day. But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. And this is a big problem. If we could marry gravity to quantum physics and the Standard Model, we would have the theory of everything. So, very smart people came up with a new story. They asked, what is more complex than a point? A line or a string? String theory was born. What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe. This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything. Unfortunately, string theory comes with a lot of strings attached. Much of the maths involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out. So string theorists did calculations in model universes, and then try to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment. So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful at all. Science is all about experiments and predictions. If we can't do those, why should we bother with strings? It really is all about how we use it. Physics is based on maths. 2 plus 2 makes 4. This is true no matter how you feel about it. And the maths in string theory does work out. That's why string theory is still useful. Imagine that you want to build a cruise ship, but you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same, things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics. So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story. We don't yet know what the true nature of reality is, but we'll keep coming up with stories to try and find out until one day, hopefully, we do know. Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star Or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. 1. You die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014+81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a goog-old years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before then. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2. The universe today is happy and healthy, with exciting things going on. But at some point, the night will turn dark. Everything that once was will peacefully sleep forever. But what is the last thing that will ever happen, and when will it be? It turns out there is such a thing, and you probably haven't heard about it. Let's travel to the end of the universe and look at the last thing. After a messy birth, our universe was a sleepy baby, warm and dark, filled with swirling clouds of hot hydrogen and helium. The story of creation is a story of this gas and where it will end up. Shortly after, the universe got busy making the first generation of stars. They were massive and lived violent lives, forging new elements, only to release most of them when they blew up. Countless stars were born and refined the gas available in the universe, cycling matter around, each generation giving most of its gas and fresh elements to the next. But not all gas is returned. Every time a new generation of stars forms, they also make more and more red dwarfs that burn slowly and live for trillions of years. When they die, they don't give their gas back to the universe, but turn into white dwarfs. So red dwarfs lock up more gas forever. Some more gas is locked forever in other remains of dead stars, neutron stars and black holes, which is bad as it reduces the material available for new stars. Today, the universe is a great home for us and will remain so for billions of years. But most of the gas has been used up or trapped. Over 90% of the stars that will ever be born have been born already. To get to the last thing to ever happen, all other things need to happen first. The next few 100 billion years will be fun and a great time for galactic exploration. But step by step, large stars and stars like our Sun will die out. Eventually, almost all the stars will be red dwarfs slowly dying. The end of everything, but not quite. In a few trillion years, the cosmic gas will finally have run out. About 88% of the mass of every galaxy will be white dwarfs, 2% neutron stars and black holes, and about 10% gas giants and sad brown dwarf losers. White dwarfs are the corpses of old stars, not much bigger than Earth, but on average as massive as half our Sun, some even much more. This makes them the third densest objects in the universe, after neutron stars and black holes. About 1 million times denser than the Sun today. Since they used to be active stars, their surface can be as hot as 150,000 degrees. White dwarfs are dim, hot, dense spheres that don't do anything anymore. But eventually, even white dwarfs will die because they're slowly losing their heat. It takes at least 10 trillion years, more than 700 times longer than the current age of the universe. As they do their cooling down, the universe around them will irreversibly grow dark as more and more white dwarfs burn out and turn into dead husks, black dwarfs. Spheres of death as cold as space itself, invisible against the dark backdrop. Over trillions and trillions of years, every object in every galaxy is eventually either ejected into the void or its orbit decays and it will fall into the central black hole and be destroyed. In about a quintillion years, all galaxies have evaporated and every object is on its own, in the center of its own observable universe, emptiness as far as can be seen in any direction, traveling through black nothingness. Still, there are things that will happen. Black holes are dying, slowly. They'll fizzle away by emitting Hawking radiation until they're so small that they die in a final flash of light. This will take about a googol years, 10 to the power of 100 years, until the last supermassive black hole dies. A number so absurd, there's nothing to compare it to. Maybe some living beings could have survived around black holes, but even this science fiction option ends now. After this unsettling amount of time, we're not even close to the end. Now is the time of the black dwarfs. It turns out there's some weird physics going on inside the dead husk of stars. The weird physics of black dwarfs. A black dwarf is a sphere the size of Earth, as massive as a star, but almost as cold as absolute zero. Stars stay alive because of their intense heat in their cores, so why do black dwarfs not collapse into a black hole? What keeps them together? Deep inside a black dwarf, matter is squeezed to densities millions of times greater than anything we see on Earth. The pressure is so great that electrons can't combine with the nuclei to form atoms. Instead, matter is weird, degenerate. The nuclei are compressed by the weight of the star, locked into a rigid lattice, while the electrons form a plasma between them. And these electrons hold the star together. We're simplifying, but imagine matter as a subway train and electrons as passengers. If there are empty seats, passengers spread out because they care a lot about their personal space. But as a black dwarf is so incredibly dense, this is like squishing more and more passengers into our train. Gravity is pushing in, trying to collapse it. The passengers are forced to sit and stand close together, which they hate. And so the passengers, our electrons, try to push out against gravity as hard as they can. This way, the electrons that are having a horrible time in the crowded train that's the black dwarf hold up the star. Everything else in the universe may have crumbled already, but these tiny particles push against each other until the end of time. Or they would, if quantum mechanics didn't ruin everything. Simplifying a lot, when particles get close enough, sometimes they can jump at each other and fuse together, a process called quantum tunneling. This happens constantly in stars because of their intense heat. It's one of the key reasons stars can fuse elements into new ones. But it also happens at a temperature near absolute zero, just, well, mind-numbingly slowly. This is the final step to creating the last interesting thing to ever happen in our universe. Here, in this lone black dwarf, something fantastic occurs. Nothing happens for 1 trillion years. Nothing at all. Can you imagine that? But then, a single fusion reaction. 2 carbon nuclei combine by quantum tunneling to become magnesium. Another 100 trillion years pass. It happens again. Then nothing for another bazillion years. Oh, 2 oxygen nuclei combine into silicon. As eons pass, the nuclei in the frozen black dwarf slowly combine, making new heavier nuclei. And these take even longer to fuse, but given enough time, they eventually will. Remember the breathtaking amount of time it took for a supermassive black hole to evaporate? That's a brief moment in comparison to what's going on here. The difference between a second and trillions of years has lost all meaning. Over a time so absurd that it has no name, nuclei keep fusing into heavier elements. Until, when silicon nuclei fuse, they form nickel-56. Nickel-56 is radioactive, which means it's unstable. And when it eventually decays and turns into iron, it emits 2 positrons, antimatter electrons. And these 2 positrons find 2 electrons and annihilate them and themselves. Which is a problem. Remember how the uncomfortable electrons produce the pressure to hold the star together? Destroying the electron means fewer friends to help them hold up the star. Losing an electron does not give them more space to scratch their butts, it just makes gravity squeeze harder, the walls closing in on those that remain. In the case of the most massive black dwarfs, this is catastrophic. Bit by bit, the black dwarf turns into a sphere of iron and more electrons are annihilated. For at least 10 to the power of 1,000 years, almost but not quite forever, there's no visible change in the entire universe. And then, finally, the last thing to ever happen happens. The black dwarf has lost 1 too many electrons. It can no longer support its immense mass and goes into an uncontrolled collapse, a supernova. It first implodes and then explodes as bright as a galaxy and fills the empty universe with light again. A beautiful moment nobody will get to enjoy. And then, as quickly as it began, it's all over. Darkness again. Emptiness. If you saw a wormhole in reality, it would appear round, spherical, a bit like a black hole. Light from the other side passes through and gives you a window to a faraway place. Once crossed, the other side comes fully into view, with your old home now receding into that shimmering spherical window. But are wormholes real, or are they just magic disguised as physics and maths? If they are real, how do they work, and where can we find them? For most of human history, we thought space was pretty simple, a big flat stage where the events of the universe unfold. Even if you take down the set of planets and stars, there's still something left. That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that. It says that space and time make up that stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it. If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic space can be bent and maybe even torn and patched together, which could make wormholes possible. Let's see what that would look like in 2D. Our universe is like a big flat sheet. Bent in just the right way, wormholes could connect 2 very, very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. So, where can we find a wormhole? Presently, only on paper. General relativity says they might be possible, but that doesn't mean they have to exist. General relativity is a mathematical theory. It's a set of equations that have many possible answers, but not all maths describes reality. But they are theoretically possible, and there are different kinds. The first kind of wormholes to be theorized were Einstein-Rosen bridges. They describe every black hole as a sort of portal to an infinite parallel universe. Let's try to picture them in 2D again. Empty space-time is flat, but curved by objects on it. If we compress that object, space-time gets more curved around it. Eventually, space-time becomes so warped that it has no choice but to collapse into a black hole. A one-way barrier forms, the event horizon, which anything can enter, but nothing can escape, trapped forever at the singularity at its core. But maybe there is no singularity here. One possibility is that the other side of the event horizon looks a bit like our universe again, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole. In the parallel universe with backwards time, the mirror black hole is spewing things out a bit like a Big Bang. This is called a white hole. Unfortunately, Einstein-Rosen bridges can't actually be crossed. It takes an infinite amount of time to cross over to the opposite universe, and they crimp shut in the middle. If you go into a black hole, you won't become the stuff coming out of the white hole. You'll only become dead. So, to travel the cosmos in the blink of an eye, humans need a different kind of wormhole, a traversable wormhole. If string theory, or one of its variations, is the correct description of our universe, then we could be lucky, and our universe might even have a tangled web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scales, far, far smaller than an atom, may have created many, many traversable wormholes. Threaded through them are strings, called cosmic strings. In the first billionth of a trillionth of a second after the Big Bang, the ends of these tiny, tiny wormholes were pulled light years apart, scattering them through the universe. If wormholes were made in the early universe, whether with cosmic strings or some other way, they could be all over, just waiting to be discovered. One might even be closer than we realize. From the outside, black holes and wormholes can look very similar, leading some physicists to suggest the supermassive black holes in the center of galaxies are actually wormholes. It will be very hard to go all the way to the center of the Milky Way to find out though, but that's okay. There might be an equally extremely hard way to get our hands on a wormhole. We could try to make one. To be traversable and useful, there are a few properties we want a wormhole to have. First, it must obviously connect two distant parts of space-time, like your bedroom and the bathroom, or Earth and Jupiter. Second, it should not contain any event horizons which would block two-way travel. Third, it should be sufficiently sized so that the gravitational forces don't kill human travelers. The biggest problem we have to solve is keeping our wormholes open. No matter how we make wormholes, gravity tries to close them. Gravity wants to pinch it closed and cut the bridge, leaving only black holes at the ends. Whether it's a traversable wormhole with both ends in ours, or a wormhole to another universe, it will try to close unless we have something propping it open. For very old string theory wormholes, that's the cosmic strings job. For man-made wormholes, we need a new ingredient: exotic matter. This isn't anything like we find on Earth or even antimatter. It's something totally new and different and exciting with crazy properties like nothing that's ever been seen before. Exotic matter is stuff that has negative mass. Positive mass, like people and planets and everything else in the universe, is attractive because of gravity. But negative mass would be repulsive. It would push you away. This makes a kind of anti-gravity that props open our wormholes. And exotic matter must exert enormous pressure to push space-time open, greater even than the pressure at the centers of neutron stars. With exotic matter, we could weave space-time however we see fit. We may even have a candidate for this exotic matter, the vacuum of space itself. Quantum fluctuations in empty space are constantly creating pairs of particles and antiparticles only for them to be annihilated an instant later. The vacuum of space is boiling with them, and we can already manipulate them to produce an effect similar to the negative mass we're looking for. We could use this to stabilize our wormholes. Once we're keeping it open, the ends would start together, so we'd have to move them around to interesting places. We could start by wiring the solar system, leaving one end of each wormhole in orbit around the Earth. We could fling others into deep space. The Earth could be a wormhole hub for a vast interstellar human civilization spread over light years, but only a wormhole away. However, wormholes have a dark side. Even opening a single wormhole kind of breaks the universe in fundamental ways, potentially creating time travel paradoxes and violating the causal structure of the universe. Many scientists think that this not only means they should be impossible to make, but that it's impossible for them to exist at all. So for now, we only know that wormholes exist in our hearts and on paper in the form of equations. Life has existed on one planet for about 4 billion years, as far as we know. But it might have started right after the Big Bang, when the universe was much stranger and more fantastic than today. A universe that might have allowed life to develop absolutely anywhere. The cosmos might be full of the seeds of life, sleeping in a dead desert, waiting for a few drops of rain to explosively bloom and grow. Tiny and not so tiny aliens might be everywhere. In this video, we're going to put together two highly speculative yet scientifically grounded possibilities. Check out the scientific papers in our sources. To properly explain it, let's first look at the paradox of life on Earth. The life paradox. For its first few 100 million years, Earth was a magma hell, constantly bombarded by asteroids. But basically, the second things calmed down and the first oceans formed, life just appeared, and zillions of microbes settled every nook and cranny they found. This is kind of strange. Life on Earth seems to be almost as old as the planet itself, as if it was waiting around for an opportunity. But life didn't only appear extremely quickly. In that tiny time window, it also crossed a huge gap. To qualify as living things, even microbes need to eat, poop, grow, and multiply. To do that, they need a genome, the biological instruction manual that sets the inner workings of an organism. How dead things with no genome become living things with genomes is one of the biggest riddles of science. Simplifying a lot, the problem is that to have a functioning genome, you need proteins, and to make those proteins, you need a functioning genome. Both proteins and genomes are super long molecules made of pretty complex blocks that are extremely difficult to assemble by chance. It's a chicken-egg paradox with several chickens and eggs. Once you have a finished cell, the whole system works efficiently. But starting from simple dead stuff and reaching that level of sophistication by pure chance should require an amazing amount of time for trial and error. So how did the first living things manage to cross that gap in just a few 100 million years? Most theories about the origin of life try to explain that gap by theorizing how some primitive soup of prebiotic molecules could have efficiently produced the first self-replicating entities. But we still don't know how exactly this would have worked. Maybe we need to think backwards. The clock of evolution. Think of genomes as a book telling the history of life. As time passed and life evolved, more characters were introduced. Amoeba, fish, amphibians, dinosaurs, and mammals. Over billions of years, the story of life got more and more complex. A genome can be viewed as a long string of letters with biological instructions. And from microbes to us today, functional genomes seem to have been increasing in size at a fairly constant rate. The functional genome of fish is more than twice that of worms. Our functional genome is about twice bigger than that of fish, and so on. It is a bit more complicated, but for now, let's run with this. When we put all these clues together, it seems that genomes have been doubling in size on average every 350 million years or so, as if evolution had been following an exponential inner clock. But it gets even stranger. The very first microbes that emerged on Earth even if they look simple, already seem to have had pretty long and complex genomes. But how could life have achieved that level of complexity in such a short time? There may be an interesting way to solve this riddle. We just take our exponential clock and extrapolate it back in time to the simplest conceivable life form. Something equivalent to a being with a genome containing just a few letters. But if we do that, we end up 10 billion years in the past, more than twice the age of Earth, which means if life actually evolved like this, it didn't start here, but somewhere out there, in space. This would explain why life started to thrive so quickly on our young planet. If it was already present in space like a seed, it just needed water and warm temperatures to wake up and go on evolving. And it would also explain the high degree of sophistication of the first life forms on Earth. They could have been complex already because they might have been evolving for billions of years somewhere else in the universe. But could life really be that old? Maybe, yes. Actually, life could have started shortly after the universe itself was born. A Goldilocks baby universe. At its most basic level, life needs two things: the right chemical elements to form complex molecules and a liquid medium, like water, in which those molecules can move and interact. The liquid medium needs to stay warm enough to remain, well, liquid. So when we search for life in space, we focus on Earth-like planets at just the right distance from their star, warm enough to sustain liquid water. But there was actually a time when almost all of the universe might have been habitable. Right after the Big Bang, the universe was extremely hot. But as the cosmos expanded, it cooled. And between about 10 and 17 million years after the Big Bang, when the universe was 1,000 times younger than today, it was between 100 degrees Celsius and 0 degrees Celsius, the temperature at which water is liquid. So for this window of time, more than 13.7 billion years ago, the whole universe, absolutely every inch of it, had the right temperature to support life. Of course, the right temperature alone is not enough for life. We also need chemical elements like carbon and oxygen, which are forged in the cores of stars. But were there stars in super early cosmic times? Maybe, yes, in regions of the universe where matter was especially dense. Such stars would have been very massive and gone supernova in just 3 million years, seeding the baby universe with the chemical elements needed to form dust, asteroids, planets, and the ingredients of life. Maybe the first ancestors of life were more exotic and didn't even need water, but thrived in substances like ammonia or ethane that can stay liquid at temperatures far below 0 degrees Celsius. They could have been sustained by the lingering warmth of the Big Bang for tens of millions of years longer, well into a time when we know for sure there were stars and all the chemical elements. The real magic of this idea is that while the universe today is extremely deadly and hostile, back then the conditions for life might have been basically everywhere. For a period that may have lasted several dozen million years, primordial life might have been able to emerge on any rock, even between the stars, sowing the universe with the seeds of what, billions of years later, would become bacteria, trilobites, dinosaurs, and finally us. At some point, the universe cooled down below the right temperature for life to thrive, but some of those ancestral life forms may have continued to exist in the internal warmth of the first planets, frozen in asteroids or hibernating in cosmic dust, tiny seeds roaming the cosmos waiting for new hospitable places to continue evolving. If they did, life now might be everywhere in the universe. Will we ever know? All this makes for a nice story, and while both the habitability of the baby universe and our exponential clock of life are reasonable ideas, they're still speculative. One more possibility among many others trying to explain our existence today. But if life came to Earth from outer space, then it should have seeded other places in the solar system too. Maybe there are fossils in dry riverbeds on Mars. Maybe we'll soon find life in the warm underground oceans of Enceladus or Europa. Titan has seas, rivers and lakes of ethane and methane as warm as the universe when it was 90 million years old. So finding exotic life on Titan would support the idea that life could have originated in the weird baby universe. So far, when we look out into the cosmos, we don't see anyone like us. But maybe that's because life needed 10 billion years or more to reach the level of complexity that allows for a technological species. Maybe there are millions of worlds filled with microbes, oceans full of exotic fish, and continents of bizarre animals. And maybe even others like us that just recently gained consciousness and are beginning to look at the sky, wondering if they're alone. Life could be flourishing right now in uncountable forms and in all kinds of cosmic environments. And if many of us share a common cosmic origin, we would all be part of a great cosmic family. The answer may lie in our cosmic backyard. Let's go and find out.